All right, so respected Director Sir, our foreign guest, Professor Jean-François Roch, head of the department, and the participants. So it is a great pleasure that we are commencing this GIAN course on quantum technologies. And this course was actually, the idea was, he's our Dean R&D, Professor Sudeep Mandal. He is Professor Jean-François Roch. So the idea was actually coined when I visited France before COVID, and then we somehow agreed that we will float a course, and then a lot of disruptions came, but we persistently continued, and I think I thank him for the perseverance and being patient with our system. All right, so the plan of the morning is that I will give a brief introduction to the course overview, and then followed by our head will welcome the guest, and then I will also request our Dean R&D to say a few words, and then I will request our director to welcome the guest. And Professor Jean-François Roch, he also has requested that he would like to give a brief overview of the quantum activities going on in his laboratory. All right, so let us begin with the brief overview of the course. So the course is on color centers in diamond as solid-state artificial atoms for quantum technologies from 6 to 10 October. And the course will be delivered mostly by Professor Jean-François Roch, and I am the coordinator of the course. So the broad theme of the course is that we all love diamonds. However, there are some atomic scale defects in the diamonds which are acting as a color centers. That means they emit light of specific colors. And in the course, we will discuss how these color centers work as an artificial atoms, which are quantum objects embedded inside the solid state matrix. So we will learn about various kinds of defects in the color center, especially silicon vacancy center, nitrogen vacancy centers. We will learn how do we characterize them, how do we isolate them, how do we study their different optical, spin, magnetic properties, and what are the different applications of these color centers in quantum technologies. One of the very interesting aspects is that we will also make practical demonstrations of quantum measurements. So Professor Roch will ask his team in France to do some live experiments, and we will try to broadcast that here for the participants. And in our lab also, we have a small quantum setup, so we will also take participants there, and they will be able to see the hands-on experiments, and it will strengthen their theoretical concepts. So it's both theory and experiments that will go together. And overall, this theme of the course has many applications, like generation of single photon sources, quantum sensing, magnetometry, quantum information. And these nitrogen vacancy centers in diamonds, they also have applications in biology. For example, they can probe the structure of protein precisely. There are experiments where they are able to measure the temperature within a single cell, the distribution of temperature within a single cell, and brain imaging, and so on. So the course will run for 5 days. There will be 15 lectures and tutorials. Our foreign faculty is Professor Jean-François Roch. I'm the coordinator, and we have got very good response. We have 34 different participants, mostly students and postdocs. We have participants from IIT Roped, IIT Mandi, and one participant from University of Copenhagen. There are 5 different themes of the course, each devoted to 1 day. And the uniqueness is, of course, that there will be direct exposure to the experimental techniques and hands-on experience. I would like to say a few words about Professor Jean-François Roch. He is Professor de classe exceptionnelle, which is highest ranked professor in a French university system at École Normale Supérieure Paris-Saclay, France. He has very broad research interests. He studies atomic defects in diamonds, single photon generation, nanoscale photonics, high pressure physics, subjecting material to pressures 1,000,000 times larger than the atmospheric pressure, NV magnetometry, and spin physics for quantum information. His academic trajectory is he did graduate studies 1984 to 1988 from ENS Paris-Saclay. In 1987, he passed Agrégation de Physique, which is a French national professorship competitive exam, and he secured an impressive rank 3. He did PhD in 1992 from University of Paris-Sud in France. Then he has been CNRS researcher from 92 to 96 in Institut d'Optics in the group of Philippe Granier. He was also CNRS researcher 96 to 98 in Laboratoire Castor Bruxelles in the group of Sergei Harosh. And since 1998, he is full professor at ENS Paris-Saclay. He has held various academic responsibilities. For example, from 2008 to 2011, he was director of multidisciplinary doctoral school at ENS Cachan. From 2009 to 2011, he was vice rector of ENS Cachan. From 2012 to 2017, he was director of Laboratoire Coton, Orsay, France. From 2015 to 2023, 8 years, he was elected president of Council Scientifique Restreint of ENS Paris-Saclay. From 2016 to onwards, he has been a member of the steering committee looking at the quantum technologies development in the region of France. And since 2021, he is also director of Interdisciplinary Center of Quantum Saclay, aiming at development of quantum science and technology at University of Paris-Saclay and Institut Polytechnique, Paris. He has published phenomenally. He has 150 plus publications in journals like Science, PRL, Optics Express, very reputed journals. He is routine delivering talks. He has given 100 plus invited plenary lectures in international events. He has two book chapters. He has also been awarded with numerous awards. For example, in 2024, he got Jeff Prize and Berthollet Medal of French Academy of Science. In 2021, he was elected senior member of Institute University of France. And in 2017, he was elected as Overseas Fellow, University of Cambridge, UK. So with this, I would like to extend a warm welcome, Professor Roche, to India. And I wish all the participants a happy, enjoyable quantum learning week. And I would like to thank our director and colleagues for gracing the occasion. And last but not least, we have a very dedicated organizing team in our lab, Biswajit, Nikita, Jayant, Bhupal, Priya, Pooja, Amar, Shivam. So they have put a lot of efforts in coordinating various activities. So big thanks to them. All right. Okay, so I would now request our head of the department to welcome the guest.
Very warm welcome to all of you, to Professor Rock, for coming here and for coming to deliver these lectures, set of lectures, and to all the participants and Professor Tripathi, our director, and Sudeep, our Dean R&D. And of course, the bulk of the work has been, of course, done by Kamal, who has been who consistently been organizing these GIAN conferences, which have been very, very helpful to a large number of students, of the participants, specifically from various corners of India and some abroad, as I got to know. Somebody is also joining us from the University of Copenhagen. So I would just like to say that this is indeed a very nice topic, because we take great pride in our interdisciplinary part of our curriculum here at IISER Mohali. And this particular topic kind of does that justice, because it takes quantum optics and material science and solid state physics, all these things together. So in a way, within the interdisciplinary, within the physics part of it itself, there is a various parts of it connecting together. To the participants, of course, I would like to say that this is a very good opportunity for you to listen to these lectures and also participate actively, ask questions, and discuss, because you have a world-renowned expert who is going to deliver these lectures, and with the demonstrations that are there, as Kamal pointed out, we really hope that this will help you in your future research pursuits as well. As we all know, and as you are aware of as well, that this quantum technologies is not just a future of physics, but it's also the future of technology. So how that comes about and how we can use it in various aspects is something that I hope that this particular conference with this particular school does justice to that, and I'm sure it will. I'm looking forward to it, and with a lot of fruitful discussions between both the instructors and the students and the participants. With that, I would like to again extend a very warm welcome to Professor Rock and to all other participants, and on behalf of the Department of Physics, welcome. Thank you.
So, a very warm welcome and good morning, Professor Roche, Professor Tripathi, Abhishek, and Kamal, my colleagues, and my dear students. We are starting after one of the biggest festivals of our country. We are all fresh, we are happy, and we are going to start a new course. Professor Kamal has been the coordinator of the GIAN course for the entire institute, and he coordinates of all the GIAN courses that we have in IISER Mohali. And today he is the coordinator of his own GIAN course. And I think you were doing is the second or the third one? Second one. So I am very sure that with his expertise and the expertise of the Professor Roche, who is a world-known scientist in this area, you will learn a lot. You will have a wonderful stay at IISER Mohali. Specifically, the hands-on experience will give you a lot of, what I should say, understanding of the field, and you will know much better, and in future you will apply them in different ways. I wish you a very happy stay in IISER Mohali, and one thing I will say that it's a wide campus. I know you will be busy with your coursework, but do feel to get out of this area, mix with others, talk to other scientists, talk to other people, and that will enrich you in different ways. And at the end of the course, I think you have an evaluation process also. So I wish you success in that evaluation process. I'm sure you will do well and have a great time and a wonderful experience. Enjoy the science. Thank you very much.
Welcome to India, to Chandigarh, to Mohali.
Thank you. Thank you so much.
So good morning and congratulations for getting this opportunity of interacting with one of the most eminent. Okay, I think this is okay. So congratulations to all of you for having got this opportunity of interacting with one of the world's topmost experts in the field of quantum technologies. I could see from his CV that he belongs to a class of Professor Exceptional. And this I know because way back in 1999, 2000, I had a French collaboration under this same scheme which Professor K.P. Singh has, Indo-French Center for Promotion of Advanced Scientific Research. Sefi Pra, and my collaborator was also Professor Exceptional. And therefore, I know that there are very selected few scientists, topmost scientists in France who fall into that band. And so this is highly prestigious position. So we are very fortunate that Professor Roche is here. I'm not sure how to pronounce, because I was in France, I think 3, 4 times, 5 times, but every time I had difficulty in pronouncing the French words. Since I'm not a man of physics, so I can cut some jokes. So I really appreciate what Professor K.P. Singh Kamal Priya Singh was pronouncing it, to my understanding, quite correctly. So it's very difficult for me to pronounce it correctly, because my French collaborator was Daniel Leroudoulier, but they will pronounce this Daniel Leroudoulier. So likewise here also, I came to know that when you listen to him, some French accent, you should try to understand that. I was told that there is a word called station. If you have to pronounce it in German, it's Station. And if you have to pronounce it in Italian, it is stazione. And probably in French, it is station. So, similar words, the same words, but pronunciation are quite different. And my problem became more aggravated because I spent time in Germany where they pronounce as it is written, like bus is not pronounced as bus, it is pronounced as bus. So in France, the pronunciation is quite completely different and quite complicated. Anyway, so just some amusing part apart, I think it's a great opportunity for IISER Mohali and participants from IT Mandi, IT Ropard, and IISER that Professor Roch is here, and he will be sharing his experience, some live demonstrations with you. So this endeavor of Professor K.P. Singh to organize such courses requires a kind of initiative, a kind of enthusiasm to make arrangements, to be a nodal person, to transmit knowledge to the students and seekers of knowledge in India. So I really appreciate the effort of Professor K.P. Singh in organizing this course. As you might have you have heard from him, it takes a lot of effort. And I also really appreciate Professor Roch for deciding to come back to India after a long time. I think about 25 years before he was in India, and now the India has changed quite a bit. And so if he goes around, he will be able to see the changes. But I think this city should have some French connection from Le Corbusier. I hope you'll have some time to see the creation of Le Corbusier in Chandigarh. And to all the participants, I would just submit that take maximum advantage of his presence. And I would also like to request Professor K.P. Singh and Professor Roch to enter into some kind of agreement, memorandum of understanding, so that we can have a closer interaction with Professor Roch and his group. And this institution already has a lot of strong foundations in quantum sciences, quantum technology. There are several people who are working in this area. And this kind of interaction will make our center more visible, more impactful, and more relevant for the country and its needs. So with these words, I once again welcome all of you, especially Professor Roch, and thank Professor K.P. Singh for organizing this event. Thank you.
request Jean-François Roch to please say a few words. And you want to show some?
Yes. Coming. No, 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 no. Let me see if it works. It worked before, so it should work again. Let me see. Should find it. Yes, I think it's going to arrive. Yes. Good, good, good. I think I see the problem. Let me see. It's a copy of the screen. Yes. Sorry for that. So, many thanks for all these kind words, and it's really a great pleasure to be here, and a great honor also to have been selected for the prestigious GIAN course. I think this is very important. It fosters international collaboration, it fosters exchanges, and this is certainly one thing that we need now at our time. So you actually pronounce my name very well. So Roch, it's how it should be pronounced. A little bit like it would be a K in English, rock. Like it's a little bit like that. You say Roch. Now I do agree that pronouncing French name can be very difficult. For instance, if you wouldn't have that, that would be Jean-François. And with that, it's Jean-François. So like a S. So you know, I can imagine how difficult this is. Okay, just to start, I would like just to show you a little bit the environment where we're working. So we are at the University Paris-Saclay. So the University Paris-Saclay, it's a very large university now, around 70, regarding European standard, at least 70,000 students. But it's actually it was founded something like 6-7 years ago by merging different academic institutions in France. And among them, there is actually my institution, the École Normale Supérieure of Paris-Saclay, and I will show you. So during the past years, there was a huge refurbishing work and new construction getting on. So you have here, so the campus is quite large. It's 4 kilometers of distance, and it's actually larger than downtown Paris. Downtown Paris, only 4 kilometers. Of course, there are the surroundings nearby, and there are basically 2-3 parts in this campus. Here, for instance, this is a little bit old pictures about, you see still some construction work here. That's actually the swimming pool now. And the swimming pool does exist. But then you have different academic institutions, like our school here. I will show you more detail. the École Normale Supérieure. It was before that in Cachan, and Cachan was a small town close to Paris, and we decided to move to join this big cluster when it was actually, that was when I was vice rector. The decision was taken at that time. And then there is a very famous also engineering school, which is called École Centrale, one of the two most prestigious engineering schools in France, and also all the university laboratories and teaching departments. For instance, the physics teaching department should be somewhere here, actually. That's where the physics teaching department here. So I have to go from here to here. So it's a 10-minute walk distance. And what is also important is that there will be opening next year, hopefully there will be a new metro line, which has been constructed, and that will link to Paris with fast metro link. Which unfortunately is missing at the moment. So just to tell you, and what's amazing was the fact that something when I started to work in this area for my PhD, now a long time ago, there was, all that was lens, really did not exist, and seeing that is indeed quite impressive, at least regarding our standard for making new things. This is our school. So you may, so somehow the university is a kind of umbrella, a little bit like the Cambridge and Oxford system in UK, where you have under the full university system, you have some colleges in Cambridge and Oxford. It's a little bit the same. So for instance, would be somehow a kind of college in the UK, in the English system. And here, the building opened in 2020, actually just before COVID, and that's how it's organized. So you have a large building here, where you see here the interior of the building, and our labs are located a little bit on the third floor. That's the third floor. So you will, I hope that the link will work so that you can have a tour of our lab in Paris, and at the same time we will try with my PhD students to settle some online experiments. Hopefully that should be on Thursday so that we have time to prepare that. And there's a very nice garden here, and when you enter here, you have these two blocks. One is the theater, and this is our large amphitheater, and the name of the amphitheater is Alain Aspect, since Alain Aspect was an alumni of the school and got Nobel Prize a few years after. Okay, so then you see the environment. What I'm actually doing, and it's my only responsibility, is I'm the director of a federative center that was founded for the development of quantum technologies. And somehow the center has also is affiliated to different institutions, the university, the Institut Polytechnique de Paris with the École Polytechnique de Paris. It's also a very prestigious engineering school. Two research organisms, because in France we have this dual system that mix university on one part, universities and national organism. The two national organisms that are involved is the CNRS, of course, and the Center for Atomic Energy too, which has a very strong program on for the development and quantum technology. And two other organisms of smaller size, INRIA, which is devoted to computer science, and of course there is a lot of ongoing work on the quantum computing, for instance, for the development of specific algorithm, those kind of things. And ONERA, which is an organization devoted to airspace industry, and to have a link, to establish links with the aeronautic industry. And ONERA is very active also on quantum sensing, especially for navigation, positioning, those kind of topic, and that's why they are involved in that. So I just wanted to show a little bit in what we are doing in this center. So it's not a single institute. It's spread in many laboratories. There actually gathers around 100 teams. And what's also maybe worth saying is the fact that many experiments that pioneered what is now called the second quantum revolution after the one in the 30s, where some experiments were really realized at the University of Paris-Saclay or in the neighborhood. So, of course, the first experiments for quantum entanglement and Einstein-Podolsky-Rosen test was done by Alain Aspect in 1982. Development of the first single photon source was also done by Alain Aspect and his PhD student Philippe Grangier. That was in 1986, and we started after that to do other developments of single photon source. I will show you a little bit, and apply them to quantum cryptography. Superconducting qubit was also pioneered at the Center of Atomic Energy by Daniel Estève and his team. And there's beautiful ongoing work now at the moment in this team where people used the superconducting technology that has been developed for qubit to do magnetic resonance at a single, a level of accuracy which is unbelievable, which is you can probe really a single nucleus spin detected and detect its environment. So it's beautiful experiments. And there is also a very nice and somehow connecting work on spintronics with the Nobel Prize of Albert Fert, who discovered the giant magnetic resonance. And there are also links between the quantum technologies that we are developing and spintronic community. And somehow we are working in all the different topics: quantum computing, quantum communication, quantum sensing. Most of the lectures I will do will be devoted to quantum sensing using NV centers. The development of also investigating quantum matter, and there's a nice connection. That's actually my topic at the moment, is how to use quantum sensing to probe quantum matter, and also the development of enabling technologies for those kind of research. And what is also important is to say that our center was benefit from the French National Quantum Strategy that was announced by our president, actually also in Saclay at the Center for Nanoscience and Nanotechnology a few years ago. And it's an effort that is around just around 2 billion euros that was spent on this topic. And basically, this is how it was declined in a lot of small tasks. And I'm especially involved in this program, which funds PhD and the development of quantum teaching activities. And also what we have, somehow we try to cover with the center basic science, transfer to industry, strong links with big industrial group like Thales, for instance. I'm actually worked in Thales for a few years, where we developed experiments for magnetic measurements. They were coming from the labs, as there was a very successful startup. Now it's not anymore startup. For instance, Candela, which is exploring the use of single photons for quantum computing and quantum communication, is around 200 people, and I think it's even more for Pascal, with developing quantum computing devices based on Rydberg atoms and their interaction. And this somehow is developed in 9 research labs, joint research lab between linking academic team and such industrial partners. And that's somehow the ecosystems for the development of these activities. Aside that, we developed a training program, so a PhD program first. We attribute around 30 PhD grant per year on the topic, and there are also grant funded by resources that researchers can have. And we started also an Erasmus Mundus joint master, which is funded by the European Commission, and it links the university with the Sapienza University in Rome, the University of Porto, and one foreign university outside Europe, the University of Toronto. And the student can be involved in this master program. It's a 2-year program where basically they spend a semester in one of those places with the obligation to move at one point. And within that, we organize every year to gather all the students a school, which is usually organized in Italy. Last year it was in Palermo, where all the students somehow that are spread out these different places mixed together. And within that, for instance, what we have been developing is a quantum engineering teaching lab. So somehow now we spread this activity in different, on different curriculum within the university. And basically you have practicals on test of Bell inequalities using entangled photon pairs. You have something where we are very quite proud of, because now we have an experiment where students can really work on a superconducting qubit. And now at the same time we have systems to do magnetometry with NV centers, a little bit what I will show you. The student can build a single photon source, test that it's indeed a single photon source by assembling a confocal microscope and detecting a single NV centers. And associated to that, there is a strong activity on microwaves, because microwaves, as you will see, are very important in all those kind of topics. And basically you can learn within 1 week, that's the idea, about what the basics of microwave, that's very electrical engineering, for instance. You can build a circuit, a microwave circuit, and actually you make the circuit actually by computer design, the circuit that will be this superconducting qubit. And now using such systems, for instance, you can control it in real time and operate it. And that's somehow the circuit that was built. So you design it using computer software, using some dedicated software. That was, of course, realized in a clean room facility. And then it's put in the fridge, cooled down to around 100 millikelvin. And then you can operate that with Rabi oscillations, get control, and those kind of things. And we hope this year to settle now a 2-qubit in the chip, in the superconducting chip. And using that, the students will be able to perform quantum gates, like CNOT gate or whatever, with a readout of the system. So the kind of thing that we want to do. So the main purpose of these activities is really to take things that were developed in the lab, something like 10, 20 years ago, and really now transfer it to hands-on experiments, hands-on activities. And that's very nice. That's something that I really like a lot. Okay, thank you a lot for that. Just a very quick overview.
इतने भी कह सकते हैं इसमें 5-10 मतलब रख लो 10-15% है सर। हाँ जी देखिए ना हाँ हाँ थोड़ा बीच में कर देना आप कह रहे हो है ना। कर दिया सर।
हेलो 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 हेलो।
बहुत कट रही है सर। ओके सर मैं ना माइक ना लैपटॉप के पास लेके चलता रहा। हेलो 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 हेलो। बहुत कट रही है सर।
हेलो हेलो हेलो
पता नहीं क्या हो
हेलो हेलो हेलो
गया। हेलो 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 हेलो। तब भी कट तो रही है। पहले वाले पोजीशन में ही है। अब देखना सर। हेलो 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 हेलो।
हेलो हेलो हेलो
हेलो
हेलो हेलो हेलो हेलो हेलो
hello, 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 hello. Sir, check करना. पहले इसका नंबर दोबारा से करना पड़ेगा. हेलो हेलो हेलो. आ रहा है सर, प्रॉपर आ रहा है. ऐसे इसकी वजह से नहीं होगा, चैनल चेंज हो. इसकी वजह से अभी दोबारा से डाउनलोड करना पड़ेगी कि वहाँ से एप्लीकेशन में जाके करना पड़ेगा. आ रहा है ना सर. Hello, 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 hello.
It's on. Good. Okay. Okay. Okay, so we might start. Thanks again for being interested in coming and for attending these lectures. So there will be different things that we will try to cover. I decided somehow to start from very basic stuff. So the lectures today will not be really focusing on NV centers, but a kind of reminder of spin 1/2 physics and also on magnetic resonance. Tomorrow, then we will start the lectures on color centers. And I will not start by describing this, but another defect in the solid state, which actually was thoroughly investigated in the past, which is the F center in alkalides. And basically, this is a very simple system to model, and we can learn a lot of things with that. And after, there will be a kind of straightforward connection to other kind of solid state defect, especially those of diamond. And I will review a little bit the basic properties of the NV centers and why it can be, it has been so successful for sensing applications, leading to myriads of applications and an amazingly number of team working on using this very specific defect. Also, and then we will maybe in those days, we will focus on how we can really probe magnetic field and going into the detail of that. There will be, I guess, a lab demo in Professor Kamal P. Singh lab. Then on Thursday, what I would plan to do, depending on how fast we have been, it's showing you how NV centers can be coupled to nuclear spins in the diamond. And this is very interesting for some also other kind of sensing application. And the lab demo that we will try to settle in video conference using video link will be more focusing on that. How you can play with nuclear spins using the detection of the NV centers. And on Friday, we'll discuss some emerging application, and I would especially like to discuss how we can use NV centers to probe superconductors at high pressure. And this is my current main research topic at the moment. Okay, so let's start these lectures by the wonders, I call that the wonders of spin 1/2. If you want, you can download the PDF version of that, and this is, I hope it's going to work. You tell me if this works or not. And normally, you can download the PDF file of the systems of what we are doing. It works? Good. Good, good. I try to do that. Okay, let's start by a quick reminder. Many of the applications on NV centers will be based on the Zeeman effect. The Zeeman effect is the influence of a static magnetic field on a neutral atom, and it was discovered at the early 20th centuries, in the very first years of the 20th centuries, by a Dutch professor, Peter Zeeman, in Amsterdam, who observed that the emission, that's for instance the emission of cadmium, and if you look to the spectroscopy of the emission of the line, it has a very bright line in the red. And if you now apply a magnetic field, you see that here each line is split into, in that case, 3 components. That was explained by the famous Hendrik Lorentz, and they both got the Nobel Prize in Physics for that citation in recognition of the extraordinary survey they rendered by their researchers into the influence of magnetism upon radiation phenomena. Actually, people tried to observe this magnetic field could have some effect, and very famous people tried that. Faraday tried, but didn't succeed in observing anything because the effect is very tiny, and you required very powerful spectrographs to observe that. And that was really the achievement that Zeeman was able to do, to have a very good spectrograph and be able for the first time to measure the splitting. Actually, it was not really a splitting, it was just a broadening of the line, and Lorentz explained that. And the explanation was that, of course, this was far before the event of quantum mechanics, so we just considered the influence of the magnetic field on an electrically bounded electron in the system, the famous Lorentz model of the atom. So if we now take the force applied to the electron as this one, the elastic bounding term here, and the coupling between the speed of the electron with the magnetic field, and this is a uniform magnetic field pointing in the z direction. You have very simple equation of motion here, and those equation of motion then will you can easily solve them, and there is of course just an oscillating electron at the frequency omega equals square root of k, the constant that bounds the electron in the system, divided by the mass of the electron. And for x and y, you have coupled terms that are somehow circular orbits of the electrons, and with different frequencies, omega 1 and omega 2. So you have 3 frequencies of the system. Only one frequency, omega 0, if the magnetic field is equal to 0, and now 2 other frequency appears if you apply a magnetic field. And if we now suppose that the influence of magnetic field is weak, the 2 frequencies are separated by delta omega, and delta omega is the electric charge of the electrons times the magnetic field divided by 2m. Okay, and they will come back to that. We see already some important parameter which only depend on fundamental constant, the electric charge and the mass. And that's why somehow it was something very important, because it tells us something about the interior of the atom. And now we can look to the dipoles that are induced in the atom. So we have here at omega 0 just an electron oscillating along the z direction. But if you will look at the 2 frequency omega 1 and omega 2, which with this difference delta omega, they have circular orbits, and the circular orbit is orbiting in one direction at a given frequency and the opposite direction on the other side for the other frequency. And now we simply need to take into account the radiation from these 3 independent oscillating dipoles at those 3 frequencies. And for that, we come back now to, sorry, the title is in French, but to how an oscillating dipole will radiate. That's a standard formula from electromagnetism. We take the oscillating dipole, we have the potentials, and from the potentials, we can calculate the electric field that is produced by this oscillating dipole. And from that, if we are far from the wavelength lambda, a distance far from lambda, you have very simple expression. The electric field is transverse with this formula, and the dependence over 1 over r, and just a plane wave propagating in this direction. and the magnetic field is perpendicular, as we know. This is very simple results from basic electromagnetics. And this is the oscillating of the dipole, as we can see. But what is also important is the fact that the field radiated by the dipole has a linear polarization, which is defined by the projection of the oscillating dipole onto the plane, the plane perpendicular to the propagation distance, as we know. So now, if I come back to that pictures, I just need now to see, to project the oscillating dipole onto a given plane, and that will give me specific polarization. And this is what we will show now. Once I'm here, I can now see what we have. I can look, for instance, in two different directions. I can have a look to what we see from here, Okay, I hope you see it here, from the longitudinal direction. And in that case, I will see it's here. This dipole will not be able to produce some radiating field. There will be only two circular polarization, sigma plus and sigma minus, and those are separated in frequency by delta omega, with delta omega, reminder, is the charge, the electric charge times the magnetic field over 2m. And now, if we look transversely, the field is detected on this transverse detection. We observe now linear polarization here, perpendicular linear polarization here, and linear polarization from this dipole. So we have now three lines, like what's in the picture I showed you, where one, the red emission of the cadmium atom was split into three components, and we have this, and you can have this, you can check that they are differently polarized, associated to this simple model. So what's remarkable is that there is a perfect agreement with the experiment. But how now can we model that, these results using quantum mechanics? And for that, basically, just a quick reminder about, and we will use that in the following, about the angular momentum in quantum mechanics. If we start with the orbital motion of a particle, the angular momentum is defined by the operator R, that defines the position of the atoms, times the P, the momentum, and we have these three components, Lx, Ly, Lz, and we can also use these three components to compute the L square, which is just Lx square plus Ly square plus Lz square. And in this representation of position, Lz is equivalent to h bar over E x dx d over dy minus y d over dx, acting on the wave function, defined as a position of the particle. And using that, it's a very simple exercise to show that Lx is not commuting with Ly, and there are these fundamental commutation relation linking the three components. This means that you do not have joint eigenstate if you take two components of the vector operator L, but since Lz, for instance, is also commuting with L square, then you can find a set of eigenstates which are joint eigenstates for both Lz and L square. And this is what we usually do. And we will call Lz and L square Jm, okay? Using the Dirac's notation. Okay, now this can be generalized, and now we will define an angular momentum operator J as with three components that verify the canonical relation of commutation between Jx, Gy, etc., like what we demonstrated before. So we have the joint eigenstate Jm. At that point, I do not know what J and M can be. But nevertheless, there is a theorem that tells us that since J square will have an average value over any state psi which will be positive, then all eigenvalues of J square have to be positive. And we choose at that point to write in by convention, like this one, J square acting over Jm is equal to h bar square, J plus 1, Gm, and G has to be real positive, and the same for Gz. Okay, and again, this parameter has to be again real because it is an Hermitian operator. Okay, now we introduce the ladder operator, plus minus, which are combination of x and y operator of this angular momentum, and they are Hermitian conjugate of each other with this relation. And now it's not difficult to say that if we apply those operators on Jm, then the influence of this operator is to rise or to decrease the m value by plus minus 1. Okay, this is you find that in every quantum mechanics lectures. So the action of this ladder operator, plus or minus, will create a gap, delta m equal plus minus 1, and that's why we call them ladder operator. Okay, now I will use this ladder operator to demonstrate some properties of the two main parameters G and M. Okay, so using that, since this is a positive operator, it already puts a constraint between M. M is bounded between a minimum value here and a negative and a maximum positive value that we have here. So we have this constraint for M value, okay? So at the same time, this tells me that somehow, if I take this negative, the ladder operator that decreases the M value, they're acting on this minimum M value for the ket, for the state, then I will get 0. I cannot go below, okay? M minimum is the minimum value of M. At the same time, there is a maximum value. And if I define J plus on this value, then I will have 0, okay? Okay, so, and now to determine this minimum and maximum value of the M quantum number, I can proceed as follows. I start from that which is 0. On this side, then if I act J plus, this will also be 0, okay? Because, of course, any operator acting on 0, the number will give 0, and the same on the other side. And from that, you can easily realize that by some very simple form algebra, the minimum value of M, the quantum number M, is minus J. And the same for G, sorry. And the same on the other for the maximum value of the quantum number M. So somehow now I have a relation that bounds the M quantum number. And I can use that. It's just a brief reminder of what you have learned in quantum mechanics. We can apply now, step by step, the quantum number. So if I start from here, Jj, it's a maximum value I can have. I apply J minus, get J, I will then obtain J minus 1, and I continue like that down to J minus J here, the minimum value of the quantum number M. And if we reapply this parameter, this operator, then I got 0. I can again start from this, apply now J plus, and I will go to Jj as a maximum value. So I have this chain of value, and that has to be closed. So to close that, we just need to count the number of steps we have, and that's 2J. So this is a closed chain only if 2J is an integer. So they set the different value of any angular momentum in quantum mechanics, as you know. It can be null, can be 1/2, can be 1, can be 3/2, can be 2, etc., etc. So I have this integer and half integer values that are possible. The electron spin, proton spin, as we will see, will be spin 1/2. And the NV spin will be 1, as we will see later on. Okay, now this is, and for that, I can compute, depending on the different values of J and M, the eigenvalue of J square, the operator J square, and the eigenvalue of operator Jz using this very simple formula. Okay? Now, what I can do more, again, it's some reminder of quantum mechanics, but we will have to use that after. That's what I want to take to remind you, this very simple quantum mechanics results. I can try to define now the eigenstates of angular momentum. This is, again, done using the ladder operator J plus minus acting on the state Jm. And then I have this simple formula that tells me that somehow I have this state, Jm, define an orthonormal basis of the Hilbert space associated to the angular momentum J. And the dimension will be 2J plus 1. Okay, now I come back to the orbital angular momentum and the eigenvalues of L square and Lz. We switch to spherical coordinates and we look for the wave function psi over r theta phi. And of course, what I need to take into account is how these operator L square and Lz act on this wave function defined into the spherical coordinates. Then it's simply L square, I know it's h bar L plus 1, the wave function. Lz acting on this wave function will be m, the quantum number m, times h bar times the wave function. Okay? And this can be, now I just need to remind you that the Lz operator in spherical coordinates is simply h bar over I times the partial derivative with the angle phi. Now, if I take that into account, I put this expression here, and what I obtain is that the dependence of the wave function as a function of this angle, this azimuthal angle, is simply the multiplication of psi times I times the quantum number n. So I have this very simple formula now that tells me that the wave function associated to the orbital angular momentum L is simply E exponential I m, the azimuthal angle, and a function that depends only of r, the distance to the origin, and the polar angle theta. So I have decoupled the angular dependence, radial and angular dependence. Of course, the condition for an orbital angular momentum is that if I turn by 2 pi, the wave function will come back to the same value. Okay, so psi take as function of r, polar angle theta, and azimuthal angle plus 2 pi should be the same as the one I started from. And that, of course, if I take this value, this has a constraint. M is then an integer. And since M and L differ only by an integer, then I know that the value of the orbital angular momentum L is only positive. So that tells me that somehow among the value positives, the value I obtain here, only those are possible for an orbital angular momentum. So up to now, I demonstrated that there are possibilities to get value of 1/2, 3/2, but these are not allowed due to the symmetry condition for an orbital angular momentum. Okay, now what I need to do is I want to, again, my purpose at that stage, it's really to have a quantum mechanical model of the Zeeman effect. So I know how to describe the electron circulating in the atom using the wave function I obtained. Now what I need to do is to see how the magnetic field will influence the quantum states. So for that, we need to get the Hamiltonian. And to get the Hamiltonian, this is not very difficult, but somehow it's a reminder. But somehow I will skip that. But the only purpose now is that we have in the Lorentz, using the Lorentz condition, taking into account the potential, vector potential A and Coulomb potential phi, we have this expression, okay, that you might know. And this is not so difficult to obtain. Basically, it's what you have, p squared over 2m, what you have usually but you need to modify the momentum by the potential vector. And this is just due to the fact that somehow you need to retrieve the Lorentz force. So somehow you start from the Lorentz force and you construct the Hamiltonian in a way that it will recover the Lorentz force, okay? And you identify like that the conjugate variables that you need to do. Okay, once I do that, then it's a little bit now of machinery. We suppose that we have a uniform magnetic field. So the potential vector is defined by -1/2 r times b, cross vector b. And then we have, and this, we can enter that into the expression of the Hamiltonian, taking into account the charge of the electron. And we do some simple development, and it's a little bit a few lines of calculation. You find that in whole textbooks of quantum mechanics. And basically, you separate the terms into two components. In one of the terms, it has a very simple expression. It's simply p squared minus e times 2. And these two will simplify with this one. And you see the product of the Lz, the operator, times the magnetic field. And there is a second term here, which is proportional to b squared. So we have two terms, one proportional to b and one proportional to b squared. And we can rewrite the linear term in this way. So the linear term will be a perturbation, which defined as mu b. There is a mistake. Dividing by h bar, Lz, the angular the orbital angular momentum operator times the magnetic field. And we have introduced an important parameter that we'll see quite often, which is the Bohr magneton. And the Bohr magneton is also defined only by fundamental constants, the electric charge of the electrons times h bar, the Planck constant, divided by 2m, the mass of the electron. Okay? So this is the magnetic dipole that I can associate to a single electron, and we will see how we can reobtain in a completely different way the Bohr magneton. Okay, now the second term. This term, which is proportional to b squared. Now if I can do some order of magnitude, you can easily realize that if I take, for instance, the levels of the hydrogen atoms. The hydrogen atoms are separated by energy difference of frequencies in the optical domain. And those now, if I take into account the order of magnitude of this term, it would lead to difference of energy, which is of the order of mu b times h, and that are typically depending of usual magnetic field that can be applied, and we will come back to that. They are smaller by the frequency differences associated to the Hamiltonian of the atom in vacuum. And if I now look to the second term, proportional to b squared, you can show that there is the same energy difference. So somehow, this compared to this one, it's the order of magnitude of this one compared to this one. So somehow, I can, if I remain to somehow the first order perturbation, I can only take into account this term and forget, and I can forget the terms which is proportional to b squared. And this is responsible for diamagnetism. the other, as you might know. Okay, now I'm just coming back to the influence of the magnetic field. So it just, I have different ways. Now I know how to explain how the magnetic field will impact the quantum states of the atom. The quantum states are associated to NLM. If I take, for instance, an atom like the hydrogen atom in vacuum, I apply now, and I see immediately that the perturbation corresponding to the magnetic field is diagonal in this basis of this eigenbasis of the atom. So if I write, for instance, what happens for an angular momentum L equal 1, I have these terms, and what I see is that each line now is split into 3 components. Each of those components are associated to a given value m, okay, m equal minus 1, m equals 0, and m equal plus 1. Okay, so I see now 3 lines depending 3 new eigenvalues, and somehow I can rewrite them as delta E, the difference of energy, as a function of m times j, I will come back to that, the gyromagnetic ratio, times mu b times the magnetic field. And this j factor is also called the Landé factor, and is equal to 1 in my simple explanation here. Okay? So I have 3 lines, and they are exactly where I expect them from the classical calculation that Lorentz did somehow to explain the Zeeman effect. So, and you can also show that, for instance, the transition from the ground state L equal 1, n equal 1, L equal 0, to, for instance, this line will have a linear polarization as in the classical explanation, where this one and this one, well, I change the m value by plus 1, means that somehow I need a photon which can take this extra angular momentum to couple to the atom, and this explains the secular polarization that I explained for detection in the longitudinal direction. Okay, so everything works remarkably well. I have both the classical computation, I have both, and now I have the quantum computation experiment, the quantum mechanics calculation, and they do agree. So unfortunately, there is the anomalous Zeeman effect. And the anomalous Zeeman effect is the fact that, for instance, if I take now the D line, the 2 emission line of the sodium atom, what I see is that these lines, instead of producing the amount of components that were previously odd, I could obtain either, for instance, 3 components when I looked perpendicular in the perpendicular direction to the B field. Now I see a number of components that are even, like here. I see that the line splits in another number of components that are not explained by the calculation I did before. And so that was a great puzzle at the beginning of the quantum mechanics, as you know. And for instance, there is this famous quotation of Pauli, who tells that a colleague who met me strolling rather aimlessly in the beautiful street of Copenhagen when he was staying with Niels Bohr said to me in a friendly manner, "Pauli, you look very unhappy," whereupon I answered fiercely, "How can one look happy when he is thinking about the anomalous Zeeman effect?" And the first explanation was given by the physicist Alfred Landé in 1924, very beginning of the quantum mechanics, where he said that somehow he constructed a model of the atom using, you know, the Sommerfeld, Bohr-Sommerfeld atom of model of the atoms, that somehow could explain that mj. So we could write that as mj times j as a function of this parameter times the Bohr magnetons times the magnetic field. But this now has to be a half integer. And this, you need that somehow to explain the number, the even number of components that are in the experiment. So we see now that there is half integer values that are possible somehow for the angular momentum that you need somehow to inject in the theory to explain this anomalous Zeeman effect. And the comparison with the experimental data works remarkably well. So you have, that's also an amazing feature of quantum mechanics. It provides you with calculations that are not super complicated to do, and at the end, you can have a really crucial test with the experiment, and the comparison is always very good. So this was actually the signature of the spin of the electron. Somehow you need to add something more. And Pauli said then to describe this anomalous effect, then instead of having 3 quantum number, I will add a fourth quantum number. But that fourth quantum number, on which he was able then, using the Pauli exclusion principle, to construct the atomic table of elements somehow and explain the structure of the element, no one really knew what it was. And the first we introduced somehow what it was these 2 young persons, George Uhlenbeck and Samuel Goudsmit. They were graduate students of Paul Ehrenfest in Leiden. So you have this beautiful connection between here, the work done by Pauli and the work done by these two young physicists. And basically, we have just to come back to another property, and this is very important for the following of the lectures. An angular momentum creates a magnetic dipole. There is a link between the angular momentum and a magnetic dipole. And this can be explained very simply using the classical model of an atom, which leads to the relationship connecting the magnetic dipole to the orbital angular momentum as mu vector is equal to gamma. Gamma classical is a gyromagnetic ratio times L. Okay, and if we now just do a very simple calculation, we consider that the electron orbiting around the proton, for instance, is equivalent to a current, okay? And we can use this to now reproduce the current times the surface of the coil here. It's like a little coil inside the atom, and we define the magnetic dipole by simply the product of the current intensity times the surface of the coil times the direction, the unit vector perpendicular to the surface of the coil. And we have here the magnetic dipole definition, and that can be linked to the angular momentum associated to the circular motion, and we have simply this ratio where it is minus the charge of the electron divided by 2m, and this will define the geomagnetic factor. Okay, now using rotation invariance of the theory, we can actually show that a similar relationship also holds in quantum mechanics, and in any, if you start from J, the operator J, and an angular momentum, in a proper surface of eigenstates of J, we have this ratio. It's the application of the Wigner theorem, which are associated to vector operators. We don't need to go into those details. Now, once I have this dipole and I submit it to, for instance, a magnetic field, then there will be some forces acting on that. And basically, using a very simple model of the sphere, which is, for instance, rectangular, I can show that there is a torque applying on the field. This is just the demonstration of the formula that gives the torque. The torque gamma vector is equal to the product of the magnetic dipole times cross the magnetic field B. Okay, and this has the effect to align mu of this torque wants to align mu with B. So somehow it's something you know. If I take a compass, the compass will take the direction of the magnetic field. And this is just the influence of this torque. Now I can show easily that the torque here derives somehow from a potential energy. So if I need to change the angle of the plane of the coil, I need some work to do that. And this work I have to do, for instance, if I go from a direction where the coil is in the plane of the the plane of the coil is, the magnetic field is in the plane of the coil, and I want to turn the coil by an angle alpha, then I need this work, minus mu magnetic dipoles times B cos alpha, and that tells you that you have a potential energy which is minus mu times P, cross B. Okay? And so I can come back now to the potential, the interaction, as I show you, is V that previously, that I derived from the general expression of the Hamiltonian, is simply now, can be written in this way. I can identify here the magnetic dipole induced by the B field, okay? And what I see, it's exactly the same formula. So I have somehow two ways to understand my interaction of the magnetic dipole with the magnetic field. I can come back, I can use the first principles using the Hamiltonian and do length calculation that will bring me somehow to this potential, okay? That's what I derived. But I can also have a more physical picture, which is simply the energy of the classical dipole inside the magnetic field, okay? But the rigorous way is to start from, of course, a general Hamiltonian that I wrote previously. Okay, so now I can use that. And I can also do something different. I can now try to understand how this atomic magnetic dipole will behave in the magnetic field. And for that, I know that there is this link between the angular momentum and the magnetic dipole, okay? There is this proportionality, and I know how the magnetic field acts on the magnetic dipole. It's a torque. So now, if I apply the theorem of angular momentum, then I can easily show that somehow the magnetic dipole, if it has an angle with the magnetic field, the torque will be like that, and will turn the magnetic dipole along, it will wobbles around the B-axis, and this is a precession motion, okay? And we will call that the Larmor precession of the magnetic dipole along the B-axis of the magnetic field I apply. And this, the frequency of this motion is simply, again, the geomagnetic factor times the magnetic field. And this is important to remind, because we will come back to that many times in all our calculation of magnetic resonance. Okay, and the hypothesis of Uhlenbeck and Goudsmit was the following. I take an electron of mass m with this electric charge of minus e, and I say that it rotates along its axis as an electron spin, okay? And what they say, this electron spin, which is somehow an internal, we see like the electron as a ball, and with this electric charge spinning on itself, will have an angular momentum, h bar over 2, and you have to put that somehow to explain the experiment, the anomalous Zeeman effect. Okay? So, what was the problem with that? We are still earlier than quantum mechanics, and somehow if we take this electron rotating on itself, and I compute now, and I say I take a classical model of the electron that tells me that the mass energy mc square, where c is the speed of light, is the electrostatic energy of a ball with a radius rc, and embedding the charge E of the electron. Then using this formula, I can compute the classical radius of the electron, which is of the order of 3 × 15 meter. Okay. Now I know the angular momentum, depending, of course, on how of the speed of rotation of this spinning ball. Okay, and this has to be equal to h bar over 2, taking into account what I said previously. So the speed of the equator, if I do this simple calculation, is c, the speed of light, divided by alpha. Well, alpha is the fine structure constant, which is equal to 1 over 137. So what I see is that the speed at the surface of the ball representing somehow the electron is much, much higher than the speed of light, which is, of course, impossible. And somehow we do not, this explanation by Uhlenbeck and Goudsmit has to face that issue. It's not consistent with this. And of course, somehow it was a kind of trick that they proposed to have that, and they were able also to go into fine computational details about the Zeeman effect and explain the value of J equal 2 of the dependence. But nevertheless, we have that problem. So you forget that. You say, OK, I don't mind that. This internal degree of freedom of the electron cannot be represented by this electric charge turning on itself. It's not possible. So somehow I integrate that in the theory. And it is actually Dirac that will provide the explanation where, using Dirac equation, where does it come from? And somehow it's deeply rooted in relativity. There are other ways also to explain the spin, but we forget that. OK, so now, once I have that, I had this extra degree of freedom, and I consider it, this internal degree of freedom of the electron, and I consider it as now I have to construct the Hilbert space in which that will describe this degree of freedom. OK? All that is reminder, I guess, for many of you. But somehow it's a way to start. So I can now use all what I know from my general theory of angular momentum and apply it to this very specific, very simple case of an angular momentum value equal to 1/2. And this I will not call J, but S. OK? So I change a little bit my notation. I have eigenstate of S square and SZ, which are defined by S equal 1/2 and M equal minus plus 1 or minus 1/2 or plus 1/2. And then I will call that the first state will be called plus along Z, which tells me that I have set a quantization axis in the Z direction, which is physically associated in that case to like here, to the direction of the B field. And the other state will be called minus, OK, minus Z. OK, and for that, I can compute now, use all the things I learned. So SZ in this basis is, of course, diagonal. And SZ is simply h bar over 2 sigma Z. And sigma Z is a simple 2x2 matrix, 1, 0, 0, minus 1. I can also construct the operator Sx and Sy. So for that, I use the ladder operator S plus and S minus. From this state now, I can compute S plus, S minus. There is a mistake here. I will correct it, sorry. OK. OK, I have S plus and S minus. And from that, I can compute Sx, the projection of the angular momentum vector S on the x-axis perpendicular to Z. And this is h bar over 2, again a 2x2 matrix, 0, 1, 1, 0. And this I will call sigma x. Same for the y direction. I have this formula. And now it's simply this new matrix, sigma y. And what I have here, it's the 3 components of Pauli matrices. Okay, so the spin 1/2 is associated to these 3 Pauli matrix. And the operator, Sx, Sy, and Ez are given by the Pauli matrix times h bar over 2. Okay? Now, what I can do is again use basic quantum mechanics to describe the behavior of a spin 1/2 in a static magnetic field. So for that, what I need to compute is the average value of mu, okay, as a function on a given wave function, given state psi over t. And psi over t will be described by the Schrödinger equation as I show here. This is the Schrödinger equation here, okay? So if I now use the Hilbert space that is done by combining the external degree of freedom of the atom, product the internal degree associated to the spin, I take, so now the Hamiltonian has two parts. One will describe the external degrees of motion. For instance, it can be associated to the Coulomb potential that bounds the electron to the nuclei, to the nucleus of the atom. And then I have these couple terms, the spin component, which is simply the term here, the magnetic dipole operator. I put a hat for each operator, as you have seen, times scalar product, the magnetic field. Okay? And this is simply mu z times B0. And I have now B is equal to B times mu z along the z direction, which z will be then the quantization axis. Okay, I suppose that initially the the state of the atom of the system has no correlation between the spin and the external degrees of freedom. And then as I have no coupling in this Hamiltonian between the two degrees of freedom, external and associated to the spin, we will remain in a product state. So we will have an evolution that this will go to this under the influence of this part of the Hamiltonian, and this will go to this under the influence of the Hamiltonian. As you may know, what I neglected at that stage, and that will be again important to remind when we will describe other defects in diamond, is, for instance, I forgot in this description, I do not take into account, for instance, the spin-orbit coupling. And the spin-orbit coupling, it's something that will couple now these different degrees of freedom, as we will see later on. Okay? So I do not take that into account. So with a very simple description, I have now just a separate evolution of the part of the wave function associated to the spin. And this is simply a component that will depend, that will be represented by a vector of dimension 2, which will be the projection of this part of the component onto the state psi plus and minus, describing the spin 1/2. Okay? And when I've done that, then I can now use again my equation, take into account the spin interaction with the magnetic field, which I can rewrite as a function of the Larmor frequency minus gamma B0. I remind you, the Larmor frequency, the classical image, is a frequency associated to the precession of the magnetic dipole in the system. And H will be proportional to h bar omega 0 divided by 2, the Pauli matrix sigma z. Okay? Now what I see is that the state plus and minus that describe the spin 1/2 with the z direction will remain eigenstate of this Hamiltonian describing the coupling of the spin 1/2 with the magnetic field, but now with different energies. Initially, those two states are degenerate, and when I apply the magnetic field, now those two states have energy plus minus h bar omega 0 divided by 2. If I come back to Landé rules state me that if I take any systems, like for instance an electron, then the energy will be ms Js mu b times b, mu b being the Bohr magneton. Ms is plus minus 1/2, and mu b is equal to mu e h bar over 2m. This means that somehow, if I use the spin 1/2, there is a subtlety. I need to change the value of this Landé factor. Now it has to become 2. Before, when I was only considering, for instance, an orbital angular momentum L equal 1, I had exactly this, I could describe the 3 components, the 3 energies of the system by the same formula, but in that case, J for L equal 1 was equal to 1. So I have a subtlety. I have a difference of the J value, which is 2, if I want it to be in agreement with my observation and all the calculation I have done. So this is quite bizarre. So somehow at the end you say, okay, why do I need to do that? Because somehow I have 2 here and 2 here. I can simplify and simply take into account the formula, remind the formula, which tells me that mu, the magnetic dipole associated to the spin 1/2, is equal to minus the charge of the electron. This is simply by I have a negative charge, the E charge here, divided by the mass times S, the value of the angular momentum, h bar over 2 in on projection of a given axis. But I want to keep that. And I will try to explain what is the physics behind that, to remind you a little bit. So again, the Larmor precessions tells me that. It's given as, this is the frequency difference. Okay, I've rearranged it using this geomagnetic factor of 2. At the same time, I can look to another influence of the magnetic field. We have an electric charge. So the electric charge as, the magnetic field impacts the spin of the electrons through this precession motion, or in quantum mechanics with its different eigenstates. But it can also influence the motion of the electron in the magnetic field. Okay? There is a Lorentz force acting on the electron, and for that, we have a uniform circular motion in the plane xy at a given frequency, which is a cyclotron frequency. And you see that the cyclotron frequency, which is just the classical motion of the electron in the field, is exactly the one I have from the Larmor precession. So the 2 are in agreement. That's what my calculation said. If the geomagnetic factor associated to the spin of the electron would be 1, like in the case of angular momentum L equal 1, that means that I would have a factor of 2 of difference between those 2 frequencies. Okay? So both motions are synchronized and occur at the same frequency. And remarkably, this has been checked in experiments, in measurements, realized on a single trapped electron by Hans Demmelt, who got the Nobel Prize for all this beautiful work, and Gerald Gabrielse. And they could trap, for instance, a single electron for a year and in this penning trap. And then they had the motion of the electron that could be measured by detecting somehow the influence of the charge on the different elements of the quadrupole that was used to trap the electron. And at the same time, they could measure the frequency difference with a great accuracy associated to the Zeeman effect occurring on the spin 1/2. That was spectroscopy experiment, as I will show later. So they could do the same kind of thing. They could measure independently, very accurately, the cyclotron motion, and at the same time, measure how the magnetic field applied on the electron modify the system. And for that, they could determine that indeed the 2 motions, precession and cyclotron motion, occurred at the same frequency omega 0 and omega c. But they could also, but it was not exactly, but they could also determine the value of J. If I take into account here I should put the value of J, whereas here I do not have the value of J. Okay? And by measuring with remarkable accuracy these two frequencies, they could really determine that J over 2 was not equal, was not 1, but 1 plus something. And plus something, now it can be measured with an accuracy of 10 minus 13. This is the highest accuracy that one can obtain in physics, in the measurement of a physical constant now. There are clocks, optical clocks now that have been developed, which has an accuracy at 10 minus 15, which are a little bit higher, and that can be somehow now used somehow to determine this parameter, because of course, to measure the frequency, somehow you need to synchronize your synthesizer, for instance, to a to a very accurate optical clock, because otherwise you don't know how to do it. And this is done now. This can be certainly done using these optical clock developments to even, in the future, to even higher accuracies. And to understand the difference here, you see that the difference is 1.00112, something like that, 1 or 16. This was actually done just after the Second World War by quantum electrodynamics calculation using by 3 people, Schwinger, Tomonaga, and Feynman. The first who did the calculation somehow was Schwinger, and using some very sophisticated calculation, he could explain that somehow the difference of the J value, the fact that J over 2 is not exactly 1 for the electron, has to take into account the influence of the electron with the quantized electromagnetic field that in which around him, and this is vacuum, but vacuum, as you know, in quantum mechanics, has fluctuations. And it is this, the interaction of the electron with this vacuum fluctuations of the with the quantum fluctuations of the electromagnetic vacuum that gives this value of J a little bit different than 2. Okay? And he could measure that the difference was somehow the fine constant structure divided by 2 pi plus another term as alpha square, etc., etc. So he could obtain like that a perturbative measurement. The idea was before, but somehow what was very strange at the beginning was that these perturbation theory, if you apply it for many, many terms, do not converge. It goes to infinity. And of course, that would lead to, that's not possible, physically possible. And it's Schwinger and Tomonaga and Feynman who found tricks to understand why this is not going to infinity. And Feynman did somehow introduce what are now known as the Feynman diagrams to get pictures of how to do this development on here, and getting and today this is a way somehow to measure the fine constant structure, and the fine constant structure using these developments can be determined using this calculation with this value. And what is remarkable is that the computation has an uncertainty which is larger than the one you can measure. So somehow you have an experiment that has an accuracy which is much higher than the one of what you can do even with very, very sophisticated calculation. Okay, and for instance, this value was obtained by taking account almost 1,000 Feynman diagrams into all that, and you can imagine how difficult such calculations are to describe the coupling with the quantized electromagnetic vacuum of the electron. Okay. I think we can make a quick break here for 5 minutes, and then we go to, now I know I reminded you a little bit what is the spin of an electron. Now, since we know also that the proton is a spin 1/2, what can we say about the magnetic dipole associated to the spin 1/2 of the proton? Okay, we make 5 minutes break, 5-10 minutes, and then we continue. So I know that certainly you have seen all that, but it was a way to to settle the notation and remind you a few things that we might need in the following of the course. Okay, we take 5 minutes.
It's raining very heavily. Let us go out and enjoy. We can stand outside if you prefer. We can stand outside instead. Yeah. So I was wondering, like,
The mass is not anymore the mass of the electron, but the mass of the proton. And since the proton is, of course, heavier than the electron, it tells us that the magnetic dipole of a proton will be around 2,000 times smaller than the one of the electron. Okay? So you just need to do that in principle. And so coming back to in the 30s, Stern, who after realizing the Stern and Gerlach experiment with his colleague Walter Gerlach, that was in Frankfurt, got a professorship position in Hamburg, which was very important, and he was professor there. And he wanted to measure, again, the magnetic measurement of the proton. So he went to his colleague, and his colleague, as also professor of theoretical physics in Hamburg, was Wolfgang Pauli. And Pauli told him, we know the magnetic moment of the proton because we know the difference in mass between the proton and the electron. And we know the electron magnetic moment. But if you like doing difficult experiments where you know the result in advance, go ahead, lose your time. And so Stern was always very impressed when you read his memories. He was very impressed by Pauli, but somehow he said, okay, he's a theoretician. I want to do the experiment. I don't care about his advice. And for that, he got Nobel Prize in 1943, which was attributed to him. And this is a citation for its contribution to the development of the molecular ray method and the discovery of the magnetic moment of the proton. So it's really for the discovery of the value of the magnetic moment of the proton that he got the Nobel Prize, not for the Stern and Gerlach experiment that is so important in the history of quantum mechanics. And I would like to describe the beauty of that experiment. So basically, Stern was a specialist about molecular ray, making molecular ray apparatus, atomic beams, and that was what he realized with Gerlach to measure the quantization of the electronic spin. Now you want to measure the proton, but then you can say, I have a problem then, because of course, if I take a molecule like hydrogen, then I will have interaction of the electrons orbiting in the molecules that will somehow be much higher than the one that I expect from the proton itself. Because there is this difference of 2,000, 3 orders of magnitude of difference between the magnetic moment. So how, and if I have already difficulties to measure the splitting associated to the electronic dipole, magnetic dipole, how can I measure something with an accuracy that would allow me to detect the influence of the magnetic dipole associated to the proton in the molecule? But then there was already some knowledge of quantum mechanics enough to design the experiments with hydrogen. If I take the ground state of hydrogen, L equals 0, I have 2 electrons in the symmetrical combination of the orbital L equals 0. N equals 1, L equals 0. But if I want to do that, due to Pauli exclusion principle, which was already known at that time, then you need to put, following Hund's rule also, you need to put the 2 electrons, the 2 spins, sorry, into the singlet state, okay, which in chemistry you represent by this design of the molecules. You fill the orbitals, the electronic orbitals, by 2 spins in opposite directions. This corresponds to the singlet state S equals 0 in the addition of angular momentum. So the total spin of the electrons, of the 2 electrons in the molecule is S equals 0, the singlet state. Okay? So basically, the 2 spins will not, since the 2 electronic spins are antiparallel, if there is now this inhomogeneous magnetic field applying on them, then it will have no influence on the electronic cloud. That's remarkable, okay? So somehow, there's no problem. The electronic spin is in a state where somehow you do not take that into account. The inhomogeneous magnetic field will only be applied on the proton spin. And now you have 2 protons. So again, you know the angular momentum rule, and that was already known somehow in at that stage of the development of quantum mechanics. Then you have 2 possibilities. Now the total new angular momentum associated to the 2 protons that I will call capital I is equal to 0 or 1. I had 2 spin 1/2. I can obtain either spin 0 or total spin 0 or total spin 1. Okay? Singlet state, triplet state. So now, if I apply that in a busy magnetic field along the z-axis, I will measure the projection of m for these 2 values of the total angular momentum. This will be m equals 0, okay, and no influence of the inhomogeneous magnetic field. The hydrogen molecule will go straight in the apparatus. Now here I have 3 possibilities, m equal +1, m equal 0, and m equal -1. M equal +1 will be deviated upwards, for instance. M equal -1 will be deviated downwards, and m equal 0 will go straight. So I have 3 possibilities, and what I expect compared to the Stern-Gerlach experiment is to have 3 deviations, 3 spots, and those 3 spots will be associated to now the value of the angular momentum of the magnetic dipole associated to the proton. Okay? And I need to do the experiment and measure what I have. And the result that was published in 1933 was a great surprise. It's not exactly the value that it's very different from the value that was predicted from this very simple model where I only change the value of the mass, and then instead of getting the Bohr magneton for the electron, I now have the Bohr magneton for the proton, but there is a geomagnetic factor which is somehow 2.5. And that's a big surprise somehow. Okay, I do not have the expected value. And today, the value was a little bit different, is a little bit different with the one obtained by Stern at that time. But again, it's the order of magnitude. Stern was only wrong by something like 10% with the means of the experiment. And let me remind you, he had to measure the deviation, which was something like 2,000 times smaller than the one of the Stern-Gerlach experiment. And this is the value of the magnetic dipole of the proton, which are very well tabulated now, very well known. Okay? That's fantastic when you compare the means of the experimental means at that stage. Then he said, okay, I want to do it. Now let's compare to something different. And something different, it's the magnetic moment of deuteron. Deuteron, it's like deuterium, you have hydrogen. And now I take a molecule which is consists of one hydrogen atom plus one deuterium atom, okay? And then you have one proton plus one electron. And you want to reproduce the things. What do you expect? The neutron does, in Dirac theory, the neutron has no charge. And if it has no charge, it cannot have a spin. So basically, you would expect to get the same results, either for this system and for the other one. And that's somehow perhaps what he wanted to test. And deuterium molecules were discovered in the early 30s by a chemist in Harvard, Harald Urey. And so we got some of the deuterium and could try the experiment. But then, unfortunately, couldn't do the experiment in Hamburg because in 13th of January 1933, Hitler was appointed Reich Chancellor. Immediately, there was a promulgation of law against Jewish people. Otto Stern was Jewish, and somehow at that point, there is a long story about that, but he decided to quit Germany, and he found refuge at the Carnegie Institute of Technology in Pittsburgh. But then he restarted completely to reconstruct a lab. It was a great effort. Somehow he didn't have all the support that he got in Germany, but now hopefully he got it. And together with his student, Emanuel Estermann, he was able to realize the experiment. And that was again another surprise. And the surprise was that he found that the magnetic dipole of the deuteron was different from the one that was observed, that was measured for the hydrogen. That's really remarkable. So if I come back here, this is what I have here for the proton. If I take now the deuteron, I had one neutron in the nuclei. I found a value which is very, very different. Here it's -1/2, the Bohr magneton, and now it's 0.5 times 1, even a positive value compared to the other one. And that's also not possible to explain. The difference, it's a new surprise, as I mentioned. In Dirac theory, you do not expect that adding something, a particle in the nuclei that has no charge, will modify the spin. So what's the reason for that? And that was a mystery until we understood, or it was then understood a few years afterwards, that somehow the proton and the neutrons are not single particles, elementary particles like the electron. There is, as you know, quarks in that. And it is the structure of the quarks inside this particle that provide these different values of the magnetic dipole. And today we know, of course, the magnetic moment of the neutron, and it's a little bit different than the one that was previously measured, but again, it's significantly different than the one of the proton. So to conclude this part, we have now nuclei, all nuclei that have non-zero nuclear spin will have a magnetic moment. The proton, the neutron, as I mentioned, are spin 1/2, and they have magnetic moment associated that can be measured. and I will show you how they can be measured much more accurately than the experiment that Stern realized. That's the purpose of magnetic resonance experiments. And if I take fluorine also, depending on the isotope that you consider, you will fluorine, for instance, isotope 19, will have a spin 1/2 2. Now, in the case of diamond, we will find 3 nuclei that are important. First, carbon. Carbon, if I take carbon, the natural abundancy of carbon is carbon-12, mostly, 99%, and 1% of carbon-13. Carbon-12 has no nuclear spin, so no nuclear spin associated to that. Carbon-13, you add 1 electron, then it has a nuclear spin 1/2. And this is found with 1%, and we will see why it matters for the NV centers, this abundancy of carbon-13. If I take another impurity, which is somehow intrinsic to the NV centers, it's a nitrogen atom that will be added as an impurity in the diamond lattice. Nitrogen can occur in 2 isotopes, either nitrogen-14. This is a spin 1 system, and the experiment will try to show you on Thursday will be related to the nuclear spin 1 to this isotope nitrogen-14, but you also can find nitrogen-15 with a very small abundance, below 1%, which is then associated to a spin 1/2. And if you control now the isotope that you introduce in the diamond to create the NV centers, you can use either natural abundancy, that you would get nitrogen-14 nuclear spin, or you can also use purified gas or purified systems, and then you will have, for instance, nitrogen-15, and then nuclear spin 1/2. Okay, this is important to remind for the following. Okay? But for all these nuclear spin, the nuclear magnetic moments are about 1,000 times smaller than the one of the electromagnetic moment, and I can rewrite them as this gyromagnetic ratio, gamma bar, to see that there's no simple theory explaining the value. For the case of the electron, we found that J is equal to 2, with a difference that can be measured with a remarkable accuracy. In that case, basically, it's a parameter given by nature that gave you the different values of these parameters, and that can change a lot depending on the element you consider and the isotope you consider. Okay, and there's no rule. And then you go to any formula, like given, for instance, by Brucker, and you will find all the isotopes. For instance, fluorine 19 is commonly used in chemistry for labeling and doing some NMR experiments in chemistry. Okay? To conclude that, I will introduce something that we might need for the following of the lecture dedicated to magnetic resonance, is a little, how can we get a representation of the spin 1/2, of the state associated to a spin 1/2. So we will represent the spin 1/2 state by what's called the block vector. And the block vector is simply a geometrical representation of the quantum state that we can write in this 2-dimensional Hilbert space associated to the basis plus minus. Okay? So if I take the state psi as C plus 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 C minus minus, I can rewrite them as modulus C plus exponential E phi plus plus C minus modulus exponential E phi minus minus. And these, of course, the state is normalized, telling me that these 2 components squared are equal to 1 when I add them. And I can add these 2 values for C plus. Then I can rewrite them at cos theta over 2 and sine sinus theta over 2. Sine sinus theta over 2. So now if I neglect an overall phase, which is not important for the general description of the quantum state here, I can suppose that these 2 phase parameters, phi plus and phi minus, are equal to 0. And then I can rewrite them as 2 phi is equal to 2 for phi minus, and then I can rewrite the state in this way. Now I can factorize this factor here, and if factorize this factor here, then I got this value here of the expression of the state. And this is a general expression of the spin 1/2 state, okay? Now if I look to that, it depends of two parameters, cos theta, a parameter theta, and a parameter phi, two angles. So then I can represent and use these two parameters, these two angle parameters, as the polar and azimuthal angle that will define the state onto a sphere, okay? And so somehow this state also, it's a very simple exercise to show that this state is an eigenstate of the projection of the angular momentum projected onto a vector, unitary vector, r theta or phi. And this is what I will call, this vector will be called the block vector. Okay. This vector is a block vector. Okay, this is a block vector here. Okay, and so this block vector will represent the state. And I now have this picture, okay, here. And basically, this is, here I have the general definition of the state, okay, written in the basis plus minus. I can represent it as a vector onto a sphere with radius equal to unity. And this vector has important information. The projection on x, y, and z axis is simply the mean value, the average value of the magnetic dipole or the spin onto this axis, okay? So somehow I can now, if I tell you I want to measure the projection, the average value of the projection of psi along, for instance, this axis, this is simply given geometrically by the projection here and the projection here, okay? Just the component of this block vector onto the given axis you consider. And this tells you the value of the dipole, okay? So then, if I apply, for instance, a magnetic field like that, I can have two kinds of magnetization associated to the magnetic dipole. I can have a longitudinal magnetization. This will be along the z-axis, or a transverse magnetization, which will be associated to projections of the magnetic dipole mu on the plane xy. And this is important to remind when we'll describe magnetic resonance. Okay? And this geometric representation is very useful because somehow it can be generalized to any two-state quantum system. And somehow the trick we will use with magnetic resonance is a general way to describe the qubit for quantum information, which is just the support of information using quantum mechanics resource. And the resource provided by the superposition, all superposition state created by a basis of plus minus state. Okay? And somehow, all the development of quantum technology somehow relies on different on the engineering of this qubit. And there's no, up to now, there's no one qubit which has been found much, much better than the other. There's many possibilities that have been implanted, that have been explored for those systems. So somehow how you can isolate a two-qubit, a two-state system. So you can rely on nature, and for instance, this is then, for instance, you will use ions or atoms, and you will isolate, for instance, a two-level state, a two-level system in all the levels of an atoms. And the most efficient system up to now has been Rydberg atoms, because those can couple very efficiently at long distance by the interaction, by the coupling through these giant atomic antennas they have by these very high quantum number. This is one possibility. And then you want also to use technological resources to create your qubit. And that can be done by superconducting systems, for instance. Superconducting system is fantastic, something really fantastic. You imagine it's a system condensed by matter. It embeds millions and billions of electrons. But somehow, at the end, all these electrons behave as only a two-level system. Okay? And you can remarkably control this system. That's a possibility. Something which is a little bit closer to what we described, is electronic spin, for instance, in silicon. Of course, silicon, basically, you will choose, for instance, silicon-28. Silicon-28 has no nuclear spin. That's the matrix. But then you will introduce some dopants, like phosphorus doping, like was done from the semiconductor industry. You know how to control the doping. And then this phosphorus doping somehow will be isolated spin within the silicon matrix. And then you play with this spin, and you try to couple them and to construct a device, quantum devices, using these impurities in that. And the great point is that you can, for instance, try to detect electrically the spin state of the phosphorus impurity in that. And that there has been very, very nice experiments realized along that. You can somehow use photons. Photons, for instance, a single photon using the polarization either vertical or horizontal will be also a two-level system. And you can code the information of that. The problem at the end is how you make, for instance, two photon coupled to each other. That's very difficult at the moment. We have no way to do that. We can do it a posteriori, but we do not have gates. For instance, it's not possible to construct a physical gate based directly on the interaction of two photons in a nonlinear medium, with only one photon interacting with another photon. That's not possible yet. Maybe in a few years that will happen, and then of course that will be a great step forward for all this technology, because the great advantage at photons is that you can propagate them and for long distance, and atoms or that. Of course, there are NV centers. We will speak a little bit about that. NV centers have been quite successful to get some dipole-dipole interaction, for instance, but then you need to put the two NV centers very close to each other, and this is up to now a great challenge if you want to extend the number of qubits based on NV centers that can be coupled to each other. Okay, and let me recommend this book. It's also maybe written by a French guy, Olivier Ezrati, and you can download it for free on the internet. It's 1,500 pages about all you might know, or you might want to know on quantum technologies, and it's really like there's somehow too much of information to my point of view, but somehow he do that, and there's a very good, other people are doing that, but it's a very good survey. He published that from year to year, and it's a very good survey about all the things that have been described, and it's quite clever about separating real advances, real step forwards to some buzz that companies have been promote or launch to get more funding. So it's quite nice, but nevertheless, it's interesting. So somehow, keep in mind also that all the things that we're going to describe somehow can be easily transferred to other systems, using the fact that a qubit is just somehow equivalent to a spin 1/2 in a magnetic field. I think I finished the lecture plan, what I plan to say to this morning. This afternoon, we're going to speak about how we can play with this spin, and that's the wonders of magnetic resonance. And we will remind you a little bit of calculation. It's a little bit, not yet the NV centers, but all that will be very helpful for us in the following day, tomorrow and the other days. So, and we will look to that. I don't know. So let's stop at this point for this morning. And if you have any questions or comment, I would be happy to try to answer. Just go ahead. So everything was very clear? I doubt. Okay, you might know. Yes, please. Yeah. So a system that works at room temperature is the NV center. And, and people have done work to build, for instance, a kind of 2-qubit gate based on the coupling with 2 NV centers. Okay, that was demonstrated somehow. But the problem with that, there's different problems. The problem is this is not a scalable system. You will find I will try to explain a little bit how you can control that through the implantation of, for instance, nitrogen molecules. And by chance, you will have 2 nitrogen close to each other, converted into NV centers. And those 2 NV centers are a distance between 10 nanometers from each other so that they couple to each other. And that works at room temperature. That's perfect. So you could imagine now if I would be able to have to construct an array of NV centers like that, then I would be possible, I will have those kind of systems. And that would work at room temperature. The problem with that is that unfortunately we are not able to do that. The conversion rate, the yield of creating an NV centers remains a few percent. So it's not possible to have those kind of system in a scalable way. So you will find a pair of coupled NV centers, I will show you, but you cannot scale it. Yes, but it's a good point. But again, it's a little bit the kind of limitation. So somehow, the thing that works at room temperature, but somehow also cool down, it's these systems. If you take, for instance, Rydberg atoms, with Rydberg atoms, you will have, atoms in vacuum, and they are cooled down by laser. So you do not rely on huge cryogenic systems like the one that is required for a superconducting qubit or the electron spin in silicon. The what? How it is measured now? He measured it by the. So he did that experiment, and basically was able to detect tiny splitting of the line, differences of hydrogen molecule arriving here or here, deviated upwards or downwards. And from that, he could measure, knowing the magnetic field gradient, like in the Stern-Gerlach experiment, he could measure the magnetic dipole. But somehow, what was interesting is that this was, as you have to measure this very tiny difference, it was not a very accurate measurement. So that's why this value, you only have two numbers. And the good way to measure it, and I will show that, is using magnetic resonance. And somehow it's said that Rabi was a kind of postdoc or visitor in Stern lab, and at that time he understood that. He understood that there was a clever way to measure the resonance about that, and that's what he implemented when he came back in the US in Columbia. So we'll see how this can be measured much more efficiently using magnetic resonance.
In slide 17, you had mentioned that the energy difference term is responsible for diamagnetism. Could you elaborate on that?
Oh, that's a little bit far. Yeah, this one. This one you see, it's something that couples to B square and with depends on X and Y. And now if you take, for instance, a hydrogen atom into this B square, and you a value which is to a magnetization which is in the opposite direction of the magnetic field. Okay, if you do the computation at the end. Okay, so but basically it's proportional to B. This is responsible for the diamagnetism susceptibility. I don't know if there are any other questions. Okay, so I hope it reminded you some basic things in quantum mechanics, but again, this will be somehow useful for the following. And again, this afternoon, it's not really on the NV centers, but it's a general technique. We'll see how magnetic resonance somehow is implemented, what it is. It's a reminder also. I'm sure that many of you already have lectures on this topic. And then again, we'll see somehow how this ID will be somehow introduced with the specificity of the NV centers. Okay? Thank you. And so we meet in the afternoon. It's okay with the sound?
Hello.
हेलो 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 सुनाई दे रहा है सर? हेलो हेलो माइक टेस्टिंग 1 2 3 चलो इसका कोई डिफरेंस बता सकते हो, मतलब नीचे लगाने से और कॉलर में लगाने? हाँ जी हाँ जी 1 डिग्री 1 लाइन ऑफ करके। अच्छा हेलो 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 1 2 3 हेलो सर ठीक चल रहा है अभी? हेलो सर आ रहा सही? आवाज़ नहीं आया? हेलो ऑन है सर माइक तो। स्पीकर से आवाज़ आ रही है, स्पीकर से आवाज़ आ रही है तो सर होना चाहिए ना। हेलो हाँ जी स्पीकर नहीं, मतलब वो अपने लैपटॉप के स्पीकर में आ रही है आवाज़, तो मतलब स्ट्रीम में भी तो आना चाहिए। आता हूँ सर लैपटॉप तक। कर दिया सर। अच्छा ठीक आ रही है सर अब? ओके तो उनको अच्छा अब ग्राफ थोड़ा ठीक आ रहा है, मतलब मैं करूँ? मैं यहाँ पर हेलो 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 1 2 3 ठीक आ रहा है सर? सर ठीक आ रहा है? ठीक है सर। हाँ जी हाँ जी हाँ जी। वैसे अभी ना अंदर के चैनल चुनने में कुछ छेड़ना नहीं अभी कुछ हो गया तो। डिले ज़ीरो नहीं है? डिले तो वो होती है ना सर, वो जो आवाज़ मतलब वीडियो पहले जा जाती है, डिले आवाज़ आनी चाहिए। इतने में क्या 35 तक कर दिया मुझे लगता है। ठीक है सर। हाँ जी हाँ जी यही कर सकते हैं तो। बाकी तो ठीक ही चल रहा है, वॉइस के साथ जो ये क्रोम वाला, हाँ अभी देख लेते हैं, ऑफ कर दो माइक।
It's okay? Need to wait a little bit, maybe. We can start. Okay, good. Okay, so the purpose of the second lecture is basically to remind you a little bit, to remind you something that you might also have seen before. This is a magnetic resonance and the basic principles of magnetic resonance and different kind of applications. And this will be important somehow because we will use that, these ideas, we'll implement them, we'll adapt them somehow to the specificity of the NV centers in diamond. Okay, so magnetic resonance is obtained by the superposition of two magnetic fields. There is a static magnetic field, B0, that is applied on the along the Z direction. And this magnetic field, as we have seen, will remove the degeneracy between the state plus and minus associated to this quantization axis. So this magnetic field sets the quantization axis, so a well-defined basis for the spin 1/2. And then we will superpose an oscillating magnetic field in the transverse direction. And what we'll see that this oscillating magnetic field can somehow flip the spin from state plus to any kind of other state. It can be minus state, or it can be, for instance, a coherent superposition of state plus and minus. And that's the purpose of the system. And we will see that this tool has led to a huge myriad of applications in physics, in chemistry, and in medicine. Okay, so we've already seen that before. So we did the calculation of the Larmor precession with two different approaches. The first one was classical approach. So it was simply the torque acting on a magnetic dipole associated to an angular momentum, if you remind. And we've seen also how this behavior can be obtained using the state plus and minus and their behavior in the magnetic field. So now let's consider the evolution of the spin under this Hamiltonian that, as we saw before, couples the magnetic dipole, which is an operator, mu, vector, to the static magnetic field. So we know how to write mu. Mu is simply gamma B0, gamma h bar over 2 sigma z, where sigma z is a Pauli matrix along the z direction, times B0. And what we have is coupled, if we decompose the state as C++ plus C minus minus, then we can write, we have two coupled equations for the evolution of C plus and C minus. There is a mistake here, of course, so I can maybe change it. Okay, it's corrected. Done. Sorry? The slide, you mean? Okay, I don't know, because we see them here. Ah, okay. Because here, if we see them here. Yeah, I see. But me, from here, it's visible, so I guess it's somewhere else. Because if I see them on the screen here, I mean, everything is set on my computer. Sorry? Okay. Okay, so we have those equations, and that can be solved very easily. We simply have C plus as a function of the Larmor frequency omega 0. I remind you, omega 0 is the Larmor frequency, and C minus here. So from that, we can easily get the evolution of the block vector. Remind us that the block vector is defined this way from here. So we see immediately that the block vector what's this? Ah, okay. I know. Let me see. Sorry. I have to remove that. Okay, so we see that this is the block vector here as a function of time is, if we compare this and this, we see that it is, we have this expression for the block vector. So we see that it is now processing as a function of time, depending on the evolution at the Larmor frequency omega 0. Okay, so we have the picture, the image of the behavior of the spin 1/2 on the Bloch spheres, which is simply this precession at Larmor frequency. So now what we will have, if we come back to the state, we know from the calculation we did this morning that applying the static magnetic field remove the degeneracy between state plus and minus, and there's now a frequency difference due to the Zeeman effects of h bar omega 0 between them. And we apply the magnetic field, the oscillating magnetic field with a frequency omega. So there is a frequency difference or energy difference, h bar delta, between the resonance between state plus and minus, the Bohr frequency between state plus and minus, and the applied frequency of the magnetic field, of the oscillating magnetic field. What is important is that, of course, that the oscillating magnetic field is in a direction as a component which is perpendicular to the z component. Otherwise, this field, if it's aligned on the z-axis, will have the same, will produce the same eigenstate. Those will evolve with time, but you cannot imagine to get the coupling from going, for instance, from state plus to state minus and vice versa. So we need some perpendicular component of the magnetic field to induce this coupling. And what we'll suppose also is that omega, if the order of omega 0 were close to this Larmor frequency. So now we have an Hamiltonian which is time dependent, which takes this expression, and we see that basically we have this matrix, and due to the coupling between the component, the transverse magnetic field, there is these now non-diagonal terms which are time dependent. So of course, what is not very helpful, as I state, it would be to try to search for new eigenstates, because those eigenstates will be time dependent. So it's not a good approach. So we'll use a trick for that. So basically, I can now write again the state in the Schrödinger equation, taking into account the state. You introduce it in this Schrödinger equation, and now I have to take into account the coupling between C plus and C minus due to the B1 field. So for doing that, we will try to see how we can solve it. And to solve it, there's a lot of different approach to do it. One possibility is to introduce a time-dependent basis which I put state plus tilde and state tilde minus that are defined as plus tilde is the state plus with a phase exponential e omega t over 2, and the same except as a minus sign for state minus tilde. So now, of course, I can write the state of the spin 1/2 in this new basis, which is time dependent, with new components, and I can have the transformation linking C plus tilde to C plus and C minus tilde to C minus. Okay, I can now re-inject that into the Schrödinger equation, and then I have these simple equations that are defined here as a function of the detuning between the frequency of the oscillating magnetic field and the Larmor frequency. And at that point, then we're going to do an approximation. And the approximation, I call that resonant approximation. You can also find that as rotating wave approximation, but I don't like so much this denomination. I prefer resonant approximation. The idea would be that we want to have a coupling, for instance, going to this point from C plus to C minus. And that will be induced by state B1. B1 will set the rate at which we will map, for instance, the state plus to the state minus. But then we have also these oscillating terms. And our approximation is to neglect these oscillating terms. We say this is far, if the detuning is small, that oscillates very quickly and on average will not produce any effect being able to map one state to another one. Okay, so what we simply do at that stage is to get rid of this point. This is an assumption, and after that we have to see if this assumption is valid, for instance, by taking into account the evolution we will obtain using this approximation and trying to see if indeed we were right in neglecting this quickly oscillating term. So we neglect these terms. Now we have done a huge step, a big step, because now we have an equation, coupled equations, that with a term here, which is now time independent. And this is very important. So we have now a coupling, so delta and minus delta on the axis here, on the diagonal of the matrix, and non-diagonal terms, which will couple plus and minus states, and which is depending on, which are defined by what we will call the Rabi frequency. The Rabi frequency is equivalent to the Larmor frequency. The Larmor frequency defines the coupling of the magnetic dipole with the permanent magnetic field, and the Rabi frequency is the same, but now coupling the magnetic dipole to the amplitude of the oscillating field. Okay, so now we can describe our two-level systems under this time evolution, under time-dependent magnetic field structure by an effective Hamiltonian, and this effective Hamiltonian is time independent. So we are back now formally to a Schrödinger equation for a two-level system with an effective Hamiltonian that is independent of time. For instance, like you might have already studied, for instance, by the coupling between the states of the ammonia molecule, where you say you have two states and you couple them through the tunnel effect. It's exactly the same now. And basically, we have this. And so if we see that, we are exactly in the situation that we studied before, where we have a spin 1/2, but now instead of looking at its evolution under this time-dependent magnetic field, we now look to its evolution under this effective magnetic field that is non-time, that it's independent of time. And the components of the magnetic fields there is a component along the z-axis and a component along the x-axis. And somehow, if we come back now to the structure of the magnetic field, of the precession of the spin 1/2, we can easily determine the evolution of the system. I will try to do it, provided I have enough batteries. Let's see. No, I won't have enough batteries, sorry. Okay, so let's do it like that. You will try to follow me. So first, we can consider two different situations. Let's consider first the situation where the detuning is large. Delta is large compared to omega 1. Then the magnetic field is mostly along, so this will be the z-axis, okay? And I suppose that my point here is the plus state, okay, on the Bloch sphere. And what I would like to do is, for instance, to reverse the spin, which is going from the Bloch sphere pointing up to a Bloch vector pointing down, okay? And then that will be minus state. Suppose now that I have this state. My effective magnetic field on which this vector Bloch vector 1 will precess is mostly along the z-axis, okay, like that. So it means that the Bloch vector is doing something like that, okay? So the probability of going from plus state to minus state is very small, okay? Now, suppose now we are in a situation where delta equals 0. If delta equals 0, then we are in a situation where now this effective magnetic field is transverse, is along the x-axis. And what does the Bloch vector do? What does the vector Bloch, what's its evolution? Basically, it will precess. But now it's going to precess along my left arm, so it's going to do like that. So you see, it comes to the minus, there is a reversal, goes to the minus state, and then come back, then I have problems, to the plus state and back and forth. Okay, so I have using this Bloch sphere evolution and this effective magnetic field, I can very simply describe the time evolution of the system. And if I want, I can also solve all equations. This is exactly what we did before. And we can determine, for instance, very easily, the probability starting from state plus to go into the state minus is simply the projection of psi that will be modulus square of C minus tilde square. Okay? So I can plot those probabilities. So this is simply C minus. I can perhaps write it down here. Let me write it down. Yes, good. Okay. Okay. Now I write down the probability from going plus state to minus state, with the initial state being plus state. Okay. So this is simply this modulus square of this component for the quantum for the state, and I have this well-known formula, which is just describe the Rabi oscillation. And again, when you are far detuned, delta, for instance, is equal to 3 times omega 1. Then you have fast oscillations, but a small probability to go from state to go to the state minus. And this is the evolution that I mentioned: fast precession with an effective magnetic field almost along the z-axis. Now, when I'm at resonance, delta is equal 0. So now the effective magnetic field like that, I have a probability of unity of going to the minus state. This is what I see here. This is the first part of the Rabi oscillation. Then I come back to state minus, to state plus, etc., and I see those Rabi oscillations. So that's what we see. Now, if I look to the probability, to the maximum value of the probability as a function of the detuning that I see here, depending of omega 1. This should be omega 1, I'm sorry. Then I can, the maximum probability of going from plus to minus is a Lorentzian as a function of delta, the detuning, and a width of 2 omega 1. This means that somehow, if I want to find the resonance, I need, for instance, this probability will become larger and larger if I increase the strength, the amplitude of the magnetic field. So this is a well-known phenomenon. It's called intensity broadening or amplitude broadening. I increase the driving field, the amplitude of the driving field, in that case B1, and then the transition becomes larger and larger and larger. And I can easily, for instance, find it. And then I will reduce the amplitude of the B1 field, and then I can point out, I can sort the resonance with an increasing accuracy this way. Okay? And this is well-known phenomena called, again, for power broadening, amplitude broadening, those kind of things. That's important. We will come back to that. You can, using this time evolution at resonance, we have we can apply a pulse of the oscillating field, and we'll define different type of pulse, and that will be also very important for the following. Pulse pi will map the state plus into the state minus. So there will be a reversal of the block vector, and if we now have the image of a magnetization associated to an ensemble of magnetic dipole behaving the same way, that would create a magnetization along the z-axis. I will call that longitudinal magnetization or longitudinal magnetic moment. Okay? So playing with the pulse P, it's somehow a way to you can imagine that I have a kind of a magnet pointing up with north pole pointing up, and I reverse the magnet. Okay? Now I can also define a pulse pi over 2. A pulse pi over 2 will transform state plus into a superposition of plus and minus state, so that, for instance, we start like that, and basically we arrive in this direction, and this would be, for instance, the state plus plus minus. Okay, or depending on the evolution. And so I transfer now the block vector into the transverse plane, and now it's like having a magnet pointing up and transferring the magnet on an horizontal plane perpendicular to its horizontal direction. Okay? So basically this is what we will do. And we will use that for a coherent drive of spin, and this will be important for measurement scheme with the NV centers. Okay, I can try to see this evolution now if I come back to my initial state, to the initial frame, sorry, because as I told you, there is two components. There is the precession at the Larmor frequency and the evolution at omega 1 that I mentioned before. So if I combine that, I can have the image of the block vector evolution in that, and which is basically this precession, and at the same time, a slow rotation going, for instance, to plus minus, to plus state, to minus state at resonance. And this is what I tried, what we observed in this very simple, what we observed in this very simple situation. We start with a block vector like that. There is a Larmor frequency, and at the same time, you see that the Z component is now turning, the component in the transverse field is like a compass which is oscillating at that frequency. Okay? And it's oscillating at, if I come back to that, when you see, it's oscillating at the Larmor frequency. This is important. Okay? So keep that in mind. Yes?
The Rabi frequency is the larger frequency in the rotating plane?
So the rotate, that's somehow what people will say. The trick we use, we can say in this Larmor frequency would be like following the block vector, you know. and that's what people say the rotating wave approximation. If that, I would be in a frame of reference in which I follow this natural evolution of the block vector. Does it answer your question? Important also is to look to those resonance frequencies. Suppose I have a magnetic dipole in a magnetic field of 1 Tesla. This is rather large magnetic field. And for instance, with an electronic spin, the Larmor frequency or the resonance frequency is around 14 gigahertz. So this is in the microwave domain. So if I want to play with electronic spin, I have to apply microwave. If I now want to play with protons or nuclei and the spins of the proton and the nuclei, then taking into account the difference of mass between the electron and the proton, we have almost 2,000 of different 2 times to the 3 as a difference, and we go from gigahertz to megahertz. That means that now, if we want to manipulate nuclear spins, we have to apply radio frequency in this domain range. So that's the two type of wavelengths that we will require. Electronic spin will require microwave excitation, and nuclear spin will require radio frequency excitation. Okay, should change that. Basically, this. Okay, let's look now to first experiments. The first experiment on magnetic resonance was done by Isaac Rabi. And basically, he had the idea that, for instance, to measure, as we discussed this morning, to measure the spin of the proton, the nuclear spin of the proton, basically what you could do is use this resonance trick to know exactly where is the resonance in a well-defined magnetic field. Because if I take the formula here of here, sorry, it's here. Oh. Okay, it was before, I guess. Gamma here. And this gamma enters here in the magnetic field. So, of course, we have to find out by the condition of resonance, we can determine gamma very accurately, okay? And measure like that the magnetic dipole. So that was the idea, and I will show you how the experiment was realized. And it was realized with an accuracy much higher than what Stern could obtain by measuring the deflection of these hydrogen molecules inside an inhomogeneous magnetic field. It's somehow a much clever way, much accurate way to measure, to get the resonance and to determine the geomagnetic ratio and those parameters. And then that was done in atomic beams, so it's complicated machines that you have a beam of molecules, for instance, and you play with the spins associated to these molecules. And now there were two breakthroughs. The first, you would like now to do it, but not with spins embedded of individual molecules propagating in a molecular beam, an atomic beam, but you want to do it, for instance, with molecules in an ensemble in a liquid or solid of those kind of systems. And that was first demonstrated by Zavoysky in USSR, where at the end of the Second World War, where he had his lab transferred from Moscow to Kazan, and he was the first to observe the magnetic resonance of electronic spin in the solid state. That's electronic spin. And basically what he was doing is making the absorption of just sending a microwave onto the system and trying to observe if there is some absorption of the microwave field by the spin resonance, the spin flip-flop induced by the magnetic resonance. And independently, there were two experiments realized on the East Coast and West Coast just after the Second World War in 1946 by Felix Bloch on nuclear spins, and at the same time by Ed Purcell in Harvard by also nuclear spins. And they got Nobel Prize from these results and the breakthrough it led. And also Rabi got the Nobel Prize, and this was a citation. By this method, Rabi has literally established radio relation with the world of the atomic nucleus, which is a very nice way to describe the achievement. Okay, so I will try to give you a little bit of idea of those experiments. The first one, the Rabi experiment with a molecular beam, it's basically you use spin preparation and spin detection using Stern-Gerlach-like apparatus. So basically you have two Stern and Gerlach apparatus, and you inverse them somehow. And somehow, if you do not do anything, the spin will behave on a way, and the second apparatus will compensate the behavior the other way. So somehow this compensation is you associate the spin up or down to different paths in the systems, and basically you recombine those paths on the detection point. Okay, and you measure the number of molecules or atoms you have here. Now suppose that in meanwhile, you put here a cavity here, which is resonant at a given frequency. This means that somehow the state which is plus here and which would be would have this trajectory here, now will have the compensation, between the two parts of the apparatus here, the two reversed apparatus will not work. So it means that since the compensation is not working anymore, you will lose atoms from detector D. And basically, it's what you see in this resonance signal, where you see the number of molecules being constant, and then at resonance, it suddenly drops, and after it reappears again once you are far from the resonance. The trick is not to scan the microwave or the radio frequency of the frequency. You just fix it. You build to have a strong strong resonance, a strong drive of the magnetic resonance. You make a resonant cavity at a given frequency, and what you tune is you tune the atoms. You tune the levels of the spin 1/2. And this is done by just changing the magnetic field, and for that it's very simple. You have external coil, and this external coil, you apply a current in that, and by changing the current in the coil, you change the magnetic field, the static magnetic field B0. So you tune the Bohr frequency omega 0 at a given omega 1 that is fixed, and a given frequency omega of the driving magnetic field, of the oscillating magnetic field. Okay? And using that, there were beautiful experiments. For instance, on the molecule H2, instead of having something quite broad associated to the protons, you could see actually different resonances, and all these resonances were describing the interactions between in the molecules. And you can see actually the different state associated to spin, nuclear spin. There's two protons, so you have nuclear spin, total nuclear spin capital I equal to 0 or capital I equal to 1, and this is what you observed. You observe different structures of those spins associated to that. So that led to the development of radio frequency spectroscopy for molecules, and you could have now, using these tools, there were a lot of experiments that were done to really probe the inside of a molecule. For instance, how the spin will be coupled if you take into account, for instance, the vibration of the molecule or the rotation of a diatomic molecule that would appear in the coupling of the nuclear spins inside the system. So it was really developed as a very powerful tool to go to investigate, to measure, to do the spectroscopy of molecules. Okay, now let me point something which is quite important. What is important is, should I do it now or never? No, maybe I will do it here. Yes, I will do it here. So maybe I should change that. Sorry, there are still some reminiscence of French. One important point is that when we do this, now what was the problem? The problem, if we want to apply that to a solid or liquid in which you have a lot of nuclear spins embedded. The difficulty in that case is that you cannot prepare the spins in a given initial state. In this experiment, the first apparatus somehow prepares the state, the molecules in well-defined quantum state plus minus. Okay, and you, like in the Stern-Gerlach experiment, you correlate those spin states to trajectories inside the apparatus. This is not something you can do when you looked, for instance, to a piece of liquid or to a piece of solid. So the problem is that then the thermal equilibrium, you can only rely on the thermal equilibrium at temperature T to create a difference between the population of the state plus and minus. Because if these populations are equal, there will be the same amount of molecule doing that compared to molecules doing the opposite way. So the two will compensate and you wouldn't get any signal. Now the trick is that there is a slight difference due to thermal equilibrium. And if you take into account the frequency difference, for instance, which is obtained in a magnetic field around 1 Tesla, this is what I mentioned before, at ambient temperature, 300 Kelvin, this difference of population is very tiny, very small, 10 minus 5 orders of magnitude. So it means that you have to detect a signal which will be very weak. But the good point is that you work with macroscopic sample that embeds a large number of spin. So somehow you compensate these tiny difference between the population by investigating a large ensembles of spins. And that allows you to get a macroscopic signal, a detectable signal. But that was quite difficult. So you could do it, for instance, that's what first it was developed with electronic spin, because somehow the energy difference is larger. So this difference of population, it's of course much higher for a thermal distribution of electronic spins compared to the thermal distribution of nuclear spins. So, and an important point also, if you want to increase that, of course, to enhance the signal, you have basically two possibilities. The first one is to increase the static magnetic field amplitude, B0, because then you will have a larger difference of energy between those two states, okay? And the other possibility is to cool down, is to cool the system and to work at much lower temperature, at cryogenic temperature, and then you will also enhance the effect. But if you want to do spectroscopy under ambient condition, somehow you have to work with that. There will be trick to improve that by using different schemes to pump the system in one of those well-defined states. And we will see how this works with the NV centers. And with the NV centers, we'll see that optical pumping will allow you to prepare the state into a given state of the spin. That was found also in optical pumping scheme was found in the 60s by Alfred Kastler and Jean Brossel. And Alfred Kastler got the Nobel Prize also for this use of the optical, for the invention of optical pumping, for improving the sensitivity of NMR and EPR detection. Once we have created a population and we release the system, of course it will come back to this thermal equilibrium, and that will occur in a time duration which is called the T1 time, and this will also be important for the following. Okay, now what I want to see, okay, I realize that I can do the experiment, compensate this slight population difference by looking to an ensemble. And then I have two approaches. The one that was pursued by Ed Purcell and his team was to say each time I do a flip-flop of the spin, there is a radio frequency photon that has been absorbed. Okay? So I lose energy of the system. I transfer the spin from a lower energy state to a higher energy state. So somehow the difference of energy has to come from somewhere. It has to come from the radio frequency that is applied on that. So what you will do is simply send a radio frequency signal using, for instance, coaxial cable or something like that, and in and out, and you measure the input energy, the amplitude at the input, and you compare it to the amplitude at the output. So it's just a frequency difference. And you do it in a way with sensitive enough that you can really measure the absorption. And of course, you do it at a given frequency because you will have, like always, you will build a resonant cavity at a given radio frequency signal. And now you tune around it the Larmor frequencies of the spin by applying a static magnetic field, and you control the amplitude of B0 of the static magnetic field using current in coils. And then they could see that was done with glycerin, if I think, and they could observe the signal exactly where it was expected. The other approach was a little bit different. The other approach, led by Felix Bloch, is to see the spin really as a magnet, and somehow have oscillating magnet, if I remember, and to detect the oscillation of the magnet on a pickup coil. So you will have a pickup coil. So if I come back to that scheme here, and I have the image, you see that the transverse magnetization is doing this, okay? Turning like that. Suppose now that I put a small coil on the side, and I have this magnetization like doing that. What I will see is that the magnetic flux along, which goes through this pickup coil, will be modulated at the frequency omega, at the Larmor frequency, okay? And so you will have a modulation of the magnetic flux through the coil, okay? And if I have this modulation, I have an electromotive force that I can detect by the voltage on the coil, appearing on the coil. Okay, so the idea of Bloch is try to detect this motion of the transverse magnetization using this system. And this can be done, so it's the signal here. And maybe we hope that on Thursday, we will show you a very simple implementation of the scheme. So we will show you a basic system that can be used to detect the spin resonance for an ensemble and play using that along the Felix Bloch approach. Again, what's important to remind, it's the fact that these measurements are not projective quantum measurements. It's not like, it's a measurement that is built up on an ensemble. So you have to repeat it many, many times, and then you build the signal, and it is this signal that you will detect. It's not a single shot experiment. I cannot say in those experiments, my spin is like that, and clack, I've been able to do that. So there is a great step to do to go from those kinds of detection to a real single shot measurement where, for instance, you would like to play with the spins and do, for instance, a gate where you will control, for instance, one spin state will control another spin state, like in CNOT gate or those kind of things. And I will show you how this could be possibly done. So the detection is done on is a collective signal. And built from a response of a very large number of molecules. And this can be described using the density matrix. And that also can be used to see the evolution of the spin, taking into account the environment or the other spins fluctuating nearby. And I will try to discuss that. Okay? what can you do with this tool? So there's really remarkable applications. For instance, if you are sensitive enough, you can look to the protons inside the molecules. For instance, let us consider the molecule of ethanols. And this is a structure. You see that each protons will see different environment, different electronic cloud around him. So those protons on this side of the ethanol molecule will somehow are equivalent, okay? Whereas these protons on the other carbon atoms will see the screening will see the influence of the oxygen atoms. And this one here will see the influence, a very strong influence of the oxygen atoms. So all this now, if I apply the magnetic field, the magnetic field that is applied, the static magnetic field, will be shielded by the proton electronic environment, by the electronic cloud of the molecules. And that will shift the resonance by tiny amount, typically relative shift of the order of 10⁻⁶. So we call that usually, it is called the chemical shift. And the chemical shift is a characteristic of the molecule used. And you can determine where the protons are located inside the molecules. And you can also count how many protons are equivalent in that. And this is exactly what is observed here. You see different of resonances. A strong one, which is associated to these 3 protons. At another frequency, we see another resonance with weaker intensity, which is associated to these 2 protons, and this one, which is associated to the proton close to the bounded directly to the oxygen atoms of the molecule. So this is a very important tool, and of course, chemists have used this tool more and more efficiently to really investigate the structures of molecules that they are able to synthesize. One of the goals of NV physics is somehow to use the NV, the magnetic resonance of the electronic spin of the NV signal to try to see by hyperfine coupling we can detect somehow this kind of effect directly on the NV signal. And there were beautiful experiments, but not yet at the level of sensitivity that is competing with this kind of system that have been developed now up to extreme sensitivities. Okay, if we want to do that, I told you there is something which is the power broadening. Of course, if we want to find first the resonance, you boost the amplitude of the B1, the oscillating field. Once that allows you to set the system, but then of course it's broadened. So there's a nice way to do this spectroscopy that was found and developed, already found by Bloch, and then developed very intensively in the 90s, 80s and 90s, especially, and it led to the Nobel Prize to Richard Ernst, the development of this technique, which is called Fourier transformed NMR spectroscopy. So instead of continuously applying the radio frequency field, I will get rid of the power broadening. What I will do is that I start from the system in equilibrium, then I apply a pi over 2 pulse. The pi over 2 pulse now will create magnetization on the transverse plane, as I've seen. And what I do then? What I will do is now I release the driving field. There's only the static magnetic field. So I have the initial magnetization is like that. There is the static magnetic field along the z-axis. What does the magnetization? It just rotates in the xy plane. We are back to the situation that I described previously, where there was, this magnet spinning in the transverse plane. So if now I set a pickup coil in this way, I will get a signal that will circulate due to the modulation of the magnetic flux through this pickup coil. And this is what you see. You see this signal, but of course there will be decay process that I will discuss maybe later. perhaps not today, but later, that will have this precession to decay, that will lead to a decay of the precession. And the signal is called the free induction decay time. And using a Fourier transform of this signal, I can now determine the frequency very accurately. And this is a frequency without any power broadening effect. So it's only the pure limitation of somehow the scrambling of the coherent oscillation rotation of my assembly of dipoles. Okay? Is it clear? So this is mostly what the basics of magnetic resonance that we would like to do. And if I look to this decay, we can associate different time scale. So basically, this is the transverse oscillation, okay? And usually, the signal we will get will decay in this way. And you have to take into account different possibilities. One possibility is the fact that the magnetic field in which all my NV centers, all my spins are located can have differences. It's not perfectly homogeneous. It means that then I have different spins that precess, but at different frequencies. And of course, when I start, they are all in phase. But progressively, they get a dephasing, and at the end, everything, the signal is averaged to 0. Okay? And that occurs within a time scale that I will call T2 star time. Okay? So T2 star is the scrambling time due to the addition of spin oscillation in this inhomogeneous magnetic field, so that the precession these spins are doing occurs at slightly different frequencies. And adding those contributions, after a time, you have random phase that occurs due to this difference of frequency differences, and that gives the signal to disappear, that produces the disappearing of the signal. Somehow that's due to the apparatus itself, but I will try my best to make the magnetic field as homogeneous as possible, but there will be still some inhomogeneity. I cannot do something perfect. But nevertheless, suppose I do have something perfect. Then there is still other things that can remove the spin, that can lead to a decrease of the spin oscillation, which is, for instance, the interactions with other spins. There can be, for instance, other spins in my material that somehow will flip-flop randomly, okay? And then that will create a fluctuating magnetic field onto a given spin that I'm looking at. And this process will now, when I add them continuously, will make the signal to decay. Okay, and this is the T2 time. We also define the T1 time. The T1 time is just the time that the signal takes to come back to the equilibrium state. When I do nothing, the system will go back to the equilibrium state for the population. And usually, in condensed matter, we have these orders of magnitude. T2 star will be smaller than T2 and smaller than T1 time. And if I take, for instance, the NV centers, the T2 star will be around can be around a few microseconds. The T2 can be increased up to something like 100 of microseconds. So there is typically a factor of 10 between them, and the T1 time can be up to millisecond time. And if I cool it down, I can even go to higher time, longer time. So typically, there would be an order of magnitude of 10 in these parameters under ambient conditions. We will come back to that and illustrate that later. Okay, I think I'm going very quickly. Nevertheless, okay, once I'm here, of course, this is something very bad, because it tells you that you are limited in measuring the spin resonance here by the T2 star. Okay, so somehow something not intrinsic to the system, but something related to the quality of the magnetic field, of the static magnetic field you apply on the spin assembly. Okay? So if I want to get rid about that, there's a beautiful trick. And the beautiful trick was discovered by Erwin Hahn in the 50s, working in Berkeley. And the trick is the following. What I mentioned before, I will come back to this system. Okay, I have that. So we only look to the magnetization that is depicted in the plane. And you imagine that there is an assembly of spin, and all these spin have this motion like that, but at different frequencies. So the image taken to explain what Hahn imagined is the following. Imagine we have runners on a stadium. Each runner has its own speed. You cannot change it. And somehow this is associated to where the spin are within the magnetic field. Okay? Now there is the starter here, gives the signal so that each runner start together. All will start together. And they run, but at different frequencies. And what you see is that when you go here, you see runners occurring from here to here to here, and they are completely dispersed on the running track. Now, the starters send a new signal. And then the runners know that they have, at the same speed, to come back to the initial point. So they turn, and they go back the other way. And of course, if everything occurs at the same speed, they will come back all together at the same time in front of the starter. So somehow you have restored the order that was somehow hidden inside the system. So you just need now to find a way to apply that on our assembly of spin. And this can be done by applying pulse, a pi over 2 pulse. A pi over 2 pulse will somehow inverse the spin state. It will inverse plus to and minus 1 minus state. So somehow it will have exactly this effect. So what we will do is this. We start by a pi pulse over 2, a pi pulse, sorry, in between. So I start with a pi over 2 pulse. The pi over 2 pulse, as I mentioned, is create this in-plane magnetization. And when it processes and it decays within the time T2 star. Okay? Then we have no signal. But the spins are still continuing, and they survive until T2 time. Now, within the T2 time window, I now apply a pi pulse. The pi pulse transfers the state plus map into the state minus, and the state minus is mapped into the state plus. That's equivalent to saying to the spin, go back. Okay? And that's what they do. And basically, they refocus at a time which is 2 times the time difference between the initial pi over 2 pulse and the pi pulse. And then progressively, you see the signal here reappearing. Of course, it will decay. It will be within a window of the order of magnitude of T2 star, okay? Not far. But then this echo signal, if now I increase that, can survive until you reach the limit of the T2. Okay? And now I can really measure the intrinsic, somehow, lifetime of the spin coherence in the system, just by doing this scheme. And this is very important. This has been really a key tool for NMR spectroscopy because it allows you somehow to address different spins inside the system without the constraint of the T2 star time. And then there was very complex sequence. I will perhaps illustrate that later on, where somehow if you want to address a specific coupling for instance, between two spins, then somehow you can design a pulse sequence that will be adapted to this pulse sequence. So you can have a complex pulse sequence. That's the simplest one, but you can now improve that to somehow have more and more efficient investigating tool to address couplings between spins. This signal? Okay, I'll come back to that. This is the signal I mentioned before. Okay? You agree with that? So I see a signal, a decay, which is disappearing of the order of T2 star. But what I would like to mention is that the spin are still processing, all at their own frequency difference, at their own frequency. So what I do then by a pi pulse is that I reverse them. And the reversal of the spin obtained after the pi pulse will now lead to a refocusing of all those spins, so that at one point they will progressively recreate the initial magnetization. And this is what you see here. You see an echo signal, which is a refocusing of all the spins at a time which is simply 2 times the duration between the initial pi/2 pulse and the pi pulse that was created here. And this is exactly the image that I mentioned here. The runner on the running track starts with different speed. They spread all over, so the signal, you cannot say which is which, okay? And at one point, they run the opposite way, and they refocus at a given time, which is simply 2 times the duration between here, the initial signal, and the pulse signal that was telling them, go back. So it's exactly this idea. And you can do the mathematics. It's not so complicated. We can perhaps do it tomorrow, where we can really see all these kind of things. Okay, maybe tomorrow we can do that. Maybe you want to, because mostly I finished, I was too quick. Or I won't have many slides.
Maybe we take a small break.
Okay, we take a small break, and then we'll come back, but we will almost have finished. Okay, let's do that. Good. So, yes?
There is a small T outside.
Sorry?
So the state got conjugate now? Whatever the initial in-plane state it was, let's say psi.
Yes.
Applying the pi pulse, are we doing the conjugate of the state?
Exactly, exactly.
That's how we will the
Exactly. Exactly. It's exactly that. And we try to see that, I hope that on Thursday we will be able to show the demo experiment on that. It was a very basic scheme. So we hope to be able to see it, to show it. Yeah, sure, you're right. Because if there is a tea, just go and take the tea.
We could also give the videographer some time.
Yes. Okay, yeah, I'm going in the afternoon.
Tea or coffee?
Tea.
Chai. The analogy is very nice, the runner's analogy.
Oh, I will close it.
Yeah.
Maybe.
Transmit live.
Good. Okay, so there were questions about what the signal here is. So this is a free induction decay signal. So basically, we created the spin magnetization on the XY plane, a transverse magnetization. And then under the action of the B0 field, there is a free precession, okay? And this free precession occurs at the Larmor frequency omega 0. And then the signal decays within a time scale T2 star, which is just the time where all the spin population seeing different Larmor frequencies in the homogeneous magnetic field will be somehow averaged to 0. Okay? The collective signal. And if you want, we can do a little bit of mathematics about that. It's not super complicated.
There was one more question.
Yes, please.
Like when you turn the field and when they start reversing their direction, so how fast they can come back, and is there like any acceleration, deceleration time involved?
No, this is coherent, so this can be done very quickly. So basically, just the drive, the intensity of the drive here. It's the duration of your pulse pi, which is just determined by the B1, the amplitude of the B1. But this you can put a lot of power there, the power you have. So indeed, what you want to do experimentally is to have all those pulses as short as possible. But this is not a problem because up to a given point, but because in this pulse sequence, all the information is obtained during the free evolution of the system. When you are free, when the spin is not affected by the amplitude of the driving field. And it's exactly this idea that we'll try to implement with the NV Center. And discuss the different contribution for T1, T2 star, and T2. Okay? So just to conclude the lecture for this afternoon, I would like now to just describe very quickly something, of course, that has made magnetic resonance very famous. It's the application to imaging. And remarkably, the application to imaging, you will see it's a very simple idea. It's so simple that you may ask yourself, why people who were very clever in understanding the behavior of spin didn't thought about that. That's really something quite fascinating to have this idea. And there was a set of people, different people that contributed to the emergence of imaging with magnetic resonance. Among them, two got the Nobel Prize of Medicine 20 years ago. And I will try to explain very quickly how this works. So suppose now, let's start with a spin distribution. So what you want to do is I take this bottle, okay, and I imagine that I want to measure the spin distribution along this transverse direction here. So how can I do that? So this is my bottle, okay, this way, okay. And what I will do now, if I have a homogeneous magnetic B0 field, all the spins here, provided the point we discussed previously, will produce a given resonance signal here. Okay, at this frequency here. Sorry, I shouldn't. Everyone agrees? The contribution of all the spin along this direction here will be the same, all producing the same resonance frequency. Now what I will do is I will apply along this direction a gradient of the magnetic field. But the magnetic field is still pointing in this direction. Eh? This is the z direction. Okay, so but I will put a gradient in the x direction where I want to measure the distribution of the spin. And of course, when you're close to the bottle here, we have less spin, and then progressively you can imagine that you have this dome shape we have this special distribution of protons. But now we measure it along this direction. So I've set now a gradient of the magnetic field in the z direction. What I do then, what will be the resonance signal? You see that the resonance signal is, of course, gamma B0 plus now gamma x time the gradient of the static magnetic field along this direction. This tells me that I have established a linear relation between omega and the position along this direction. So I can now have a signal that somehow will be like that. It will be the number of spin taken into account this projection. Of course, when I look from here, I have not much spin here, and then progressively it becomes broad. There's more and more spins up to a point where I'm in the middle of the bottle, then I see a constant homogeneity. It would be like something like a square vanishing progressively when I'm on the wall of my bottle. Do you see what? So basically what I do, from this signal, I have the projection of this, and if I know exactly the gradient of the magnetic field, then it's perfect, because I can deconvolute from that and get the spatial distribution of the spins along this axis. So it's remarkable. What you do is that you encode using the gradient of the magnetic field, you encode the position x in this direction on the frequency, on the resonance frequency of the spin. And then by just measuring how many spin are the intensity of the magnetic resonance signal, you measure the number of spin at a given position x. This is simply this experiment. That's remarkable. So I can do that, for instance. This is just a trick. You can think a little bit for a while about, suppose now I have a kind of distribution. So it can be like that, let's say. Okay, I have 4 bottles, or 3 bottles, or whatever, like in the game. And now I want to detect that. And how I can do that? The idea would be to apply a magnetic field gradient in different directions. The magnetic field is still like that. But the gradient, you can apply it like that using external coils. So imagine you have a lot of coils around the system, and you can apply your gradient how you want. Like this, like this, like this, like whatever. Okay? And so now I will have, just along this signal, I will have different frequencies. Okay? And for a given direction of the gradient of the magnetic field, I will record different profile of the resonance signal. And for instance, if I use 4 projections, 4 directions of the magnetic field, I detect this. Suppose I have this signal. And now I want to determine which is the good one. It's a guess. You have different ideas around this. You can think, and I give the answer tomorrow morning. Okay? The answer will be given tomorrow, or I can do it now. So who is for 1? Who is for 2? Who is for 3? Who is for 4? No one? Who is for 5? Who is for 6? And who is for 7? You see the point? You see? So I have this. For instance, suppose like now I do that with the same bottle. Okay? Like this. Suppose I apply my magnetic field gradient in this direction. What will I see? I will see here a signal from here to here 2 times, and 1 time here. So that will be a signal with 1 peak, and a signal with the other peak associated to this bottle, a little bit further away. But this will be 2 times the amplitude of this one. Okay? Do you agree with me? Because I have 2 bottles when I do this and this. So I have a signal like 2 peaks and 1 peak. That's if I apply the magnetic field like that. Okay? Suppose I apply it like that. They're the same. I will have 2 peaks and 1 peak. Okay? Now I can also apply it like that. And then there will be 1 peak like that, and this will project onto this direction. But that will be 1 peak and the higher 2 peaks, okay, but the other one. And I can also do it like that, and that's quite interesting because if I do it like that, I will see 1 peak here, the 2 peaks going there, and another peak here that projects in between. Okay? And I will see 3 peaks in that direction. So that tells me that in this direction, if I do apply the magnetic field in this direction, I get the symmetry of the system. So I can play with that. And if you do that, then you can somehow use this information to put the signal here, you see? Like this and this and this and this and this. And then somehow you get the projection. Okay? And you know that here you will have something which is twice the intensity. Okay? And this and this and this and this. And basically you can convince yourself that it's something associated to this, this, and this. So it's something exactly what I showed you. Okay? So the signal I got, it's exactly the good one. And you can say that there are nevertheless some ghost resonances that appear here and here, which are weaker, and those are somehow a parasitic contribution. Okay? But at least you know that the configuration I show on the table here was exactly the one that produced this signal. Okay? Do you agree with me? So you can do that, and that's also one important feature of magnetic resonance imaging, of MRI, because that can be done mathematically. And you can also somehow get rid of those ghost images here using what is called an inverse radon transform. It's something like a kind of Fourier transform adapted to this situation. But somehow the idea is you want to reconstruct the shape of a 3D object, and that can be done by taking slices. And from different slices, you can reconstruct the 3D shape, okay, using different projection. And that was actually invented for the radar. So all these techniques came from the radar. And because, of course, what you want to do in radar, you have station on the ground. Those emit radio waves, radio frequency signal up to the object you want to detect, for instance, an airplane. There will be echo signal. You catch the echo signal, and using the information from different radar states coming from associated to different radio frequency, and you somehow tune them by changing the frequency. You recognize each signal coming from each station by a different frequency, then you can reconstruct the plane and get information where it comes from. So it's exactly, that was, all those techniques were actually developed for the radar, for radar. And somehow all of these people that invented NMR, it's something that is well known also, they were working for the development of radar during the Second World War, and after that they used somehow all their knowledge to develop the magnetic resonance technique in the lab for their own purposes. Okay, so now, of course, this was a very important tool, and it has been now implemented currently in hospitals, where basically you will look at the protons in water, and you use the fact that the water content of a diseased cell will be different than that of a healthy cell. Okay, and this is what you will do, for instance, to investigate if you have some disease or problem somewhere. Okay, and the resolution, of course, like that you can achieve, is of course limited by the amplitude of the gradient. And to have a gradient as high as possible for the magnetic field, you use superconducting magnet. So one of the, usually that's a machine for magnetic resonance imaging, where you have here superconducting magnet, and the patient is integrated inside. And after that, in this machine, you have a system that turns the coils, which produce an awful noise regarding these issues. And here, if you see here, there is something here, just because if there is any problem with a superconducting magnet, of course, it heats up, and the helium that is required to get to the low temperature required for the superconducting magnet then immediately evaporates. So you need somewhere to flow the helium out, and this is usually what you have here. You have a host system, exhaust system, to prevent the quenching of the, if the quenching of the superconducting coils appear, then it heats up, not superconducting anymore. Temperature rise very quickly. All the helium goes to gas, and of course you have to put an exhaust, otherwise everything explodes. You can do a lot of developments with that. For instance, what was invented, something you've seen many, certainly images associated to that. It's what called functional medical imaging. So for instance, you detect blood oxygenation using paramagnetic tracers. So we'll introduce gadolinium, for instance, ions. These gadolinium ions will actually modify the T1 time. It will shorten them because there are interaction with the ions that modify the T1 time, and you quench the signal, the magnetic resonance signal. You decrease it very significantly, and that is a way to measure somehow the paramagnetic tracer and to see how they evolve. And this is, for instance, how you can do some image of living part of your body, like for instance the brain, and seeing when you speak, what do you activate, and do those kind of fascinating images that help really greatly the development of neuroscience. In France, for instance, close to Saclay, the Center for Atomic Energy used all his savoir-faire, all his technical knowledge on the development of superconducting magnet for particle accelerators to implement one of the most powerful imaging center for MRI, which is called Neurospin, with the idea that you can really image brain and see neurodisease and those neuronal disease, those kind of things, how it occurs, or you can see language apprentissage, for instance. All this can be investigated there. Up to a given limitation, it's the spatial resolution. And the spatial resolution is, of course, set by the gradient, and typically now they are a little bit below the millimeter range. This is enough for certain application, not enough for many other applications. For instance, and one of the goals, for instance, where people have been working quite hard, is to use this kind of topic to see, for instance, if that can be applied for using NV centers. Again, I will come back to that, but there was a very nice development from my colleague with this idea, is to use, again, the same idea of a gradient of magnetic field that was done by colleagues in Thales, where you can do real-time spectral analysis of a signal. And this is, all, again, very important for all kind of recognition using radar techniques. So I will explain a little bit the implementation of this idea for other purposes, but again, how you can use the spatial encoding to analyze a signal. And it's exactly what is done, this kind of thing. There is a great also interest in doing NMR, not with big magnetic field, but on we're using small magnetic field that you can make with coils and reasonable current in coils. And this is, for instance, a French company, and the same is been developed in the US, for instance. But basically, the idea is to use very low magnetic field, below 10 millitesla, that you can easily produce with magnetic coils, and nevertheless make a kind of MRI systems that can work with approximately the same resolution as the one that you can achieve with those machines. And what is really great is that basically there's a lot of mathematics hidden. So you get signals, and after that, using a lot of clever transformation, mathematical transformation, like wavelet analysis, those kind of things, you try to retrieve the signal with a very noisy basis, but the noisy somehow is associated to the magnetic field. So if you map very carefully the structure of the magnetic field, then somehow you can improve very significantly the signal-to-noise ratio. That's a little bit the idea. So there's a lot of development, for instance, about implementing these NMR techniques at low field, using also data analysis treatment and very clever mathematical developments to get the signal out. Okay, so I would just like briefly to conclude the lecture for today, this morning and this afternoon. So what I wanted to show, basically, that NMR was first invented as a spectroscopy tool. It was used to measure the gyromagnetic factor of nuclei, and it has been also very successful for chemists to understand the structure of molecules. And this is certainly a very nice development. It has also been used also as a very important tool for solid-state physics. I should have mentioned that. For instance, the first demonstration of superconductivity was obtained using NMR. Why? Suppose you get now 2 electrons. You know that superconductivity comes from the binding of 2 electrons, for instance, with phonon in BCS theory, and I will create a Cooper pair. But this is now 2 electrons. So if I measure the NMR signal of that, I should see the spin of the 2 electrons in a way where they are, for instance, in the singlet state, total singlet state, or to produce the condensate of the Cooper pairs. So then I will see a clear difference due to the binding of the electrons in Cooper pairs compared to a single electron in the metal, for instance. So that has been very important, and NMR has been routinely used also to investigate the interior of a superconductor. You know that and I will explain that a little later on, due to the Meissner effect, the static magnetic field cannot penetrate a superconductor. So if you now have the protons inside your superconductors, they will see a screened magnetic field. So somehow you can investigate by, for instance, a kind of MRI technique, how the protons of your system will behave, and that's very important to understand the physics of the superconductor. So really, there's a lot of applications where also in solid-state physics, we have been able to use the technique coming from NMR, either use to nuclear spins or to electronic spins also, to understand really the physics of the system. And that's also very important. So it's really give you a handle on the electrons in the system. Importantly, NMR, it's an ensemble measurement, and its sensitivity is limited by the difficulty to prepare a well-defined quantum state. We rely on a thermal equilibrium. And we will see that how this can be somehow, we can circumvent that limitation, this bottleneck, by some pumping mechanism that will allow us to prepare to beat the thermal equilibrium. Okay, another point also, maybe more technical perhaps, but the calculation we did for the resonant interaction between the spin 1/2 and the oscillating magnetic field is general. You can adapt it, and for instance, this is exactly the tool for if you want to describe the interaction of a 2-level atoms with ground state and excited state with an oscillating electromagnetic wave. It's the same calculation. You simply have to change a little bit the first equations, and basically you apply the same trick and you will get the same results. So that's why the block vector is also very useful if you want to describe, for instance, how a 2-level atom interacts with an electromagnetic wave. And perhaps another more like technological consideration. NMR was really invented, I'll show you the work from Habi and others, as a fundamental research tool. And nevertheless, after that, very quickly, thanks to engineers, we have been able to exploit the precision, the accuracy, to develop instruments you can purchase an NMR spectrometer, you can purchase a nuclear imaging machine, MRI machine, and also you can refine reconstruction methods like Fourier transform, radon transform, and this also has been very important. So it has become now really an essential tool. But the time frame it takes to go from the first discovery by Habi at the end of the 30s to really first practical developments. Brucker, for instance, the NMR spectrograph from Brucker, I think, came out at the end in the 60s. It's something like 30 to 40 years. So it takes 30 to 40 years between a discovery or fundamental research to translate into a technical development. A real technical development, something that's really put on the market, that has all the features that people want. That's the time scale. Perhaps can be 20, can be, but there's very little experimental breakthrough, a technical breakthrough that are below this 20 years time scale. And this is something when you go, for instance, for the development of quantum technologies, explaining that to people that are funding the technical development is rather difficult. So it takes 20 years. And what the money you invest now in fundamental research, that will produce outcomes, and you don't know which outcomes 20 years later. That's not easy to explain. But I think if you do that, I think if you need at one point to explain this to people, I think nuclear magnetic imaging is a nice example. Nuclear magnetic MRI was people didn't thought that any kind of the magnetic resonance principles could be used to do imaging for medical purposes. And at the end, the story that just a little before his death, Rabi, who invented magnetic resonance, had to go to hospital, had this kind of medical exam in this MRI machine, and told the doctor, you know, I invented magnetic resonance, but I never have thought that this could have led to those kind of features. And exactly what perhaps need to be explained. Investing money in science, the outcome will be 20 years. Unfortunately, this is not the time frame for a politician. Politicians want to invest money and get the feedback, get benefit during the time where he is of his mandate, and this is a difficulty. Especially now in the context of quantum technology, this is commonly a problem, and we are facing that every time when we discuss with some people. Okay, we stop here today, and then tomorrow we really describe the ENVI Center.
All right, so let us thank him very much. So today's program ends here, and tomorrow we will begin at 10 o'clock.
So really tomorrow we start with diamond, okay? And that's what and we start with diamond, and we try to explain what is the structure of diamond, why diamond is maybe interesting, and it's interesting due to its defects. And we try to explain that, and then we try to make perhaps what you learn in solid-state physics, the block function for electrons. I will try to explain why this is not appropriate, why we need another very different approach to describe the physics of a point defect in a solid. That's the purpose of tomorrow's talk, and then we'll continue on the ENVI centers afterwards. Good?